You settle in as the room goes quiet, and for a moment there's only the soft electric hum of a telescope tracking a point no wider than a needle tip across the sky. Somewhere past midnight, the first image drops into a folder with a name that means nothing to sleep, only to those who watch. On the screen, a small defiant bead of light with a strange halo like breath on glass. It is July 21st, 2025, and from Hubble's patient eye, the universe has just sent us a riddle. The halo isn't where it should be. The glow leans toward the sun, not away from it. It looks as if the object is breathing against the wind. You've seen comets before. They flare, they fray, they shed. Their tails are obedient, swept outward by sunlight's pressure, and by the charged gust of the solar wind pulled into long banners that point the way comets always point away from the furnace. But this one, this interstellar vagabond we call 3 Atlas, seems to answer the sun with a forward-facing plume. In the language of comet morphologies, it sketches an anti-tail, a sunward brightness that appears to violate the simplest rule of radiance and recoil. In the language of the heart, it looks like intent. If these mysteries have you on edge the way they have me, don't just watch Join the Hunt. Hit like and subscribe so you don't miss a single revelation as this story unfolds moment by moment in real time. Tell me in the comments where you're watching, from what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. The image passes from server to eyeballs to whispers. Screens light up in kitchens and control rooms. Faces bend close. Coffee cools untouched. And in those first hours, no one says the word impossible. They say interesting. Then they say let's check, and they keep saying that until the dawn paints the edge of the world and the next observatory comes online like a relay baton lifted into a running hand. Weeks pass. The Nordic Optical Telescope watches from La Palma, night after night, its dome yawning open, to catch a traveller moving sunward on a high, open path, hyperbolic unbound. Frame by frame, the forward glow weakens as a new signature grows behind it. By late summer, the object wears the proper garment of a comet, a tail that streams anti-solar away from the star like script written by photons. Something has changed. Not all at once, not like a lamp, but like seasons and internal weather turning over. The faint skyline of the anomaly migrates from "this is odd" to "this is a pattern," and then to a question that tightens like a knot in the mind, what flips a jet inversion. The term is simple enough, an emission that once favoured one direction now favours its opposite, but the simplicity is a trap. A comet is not a neat machine with a single nozzle. It is a lumpy layered body, a frozen reef of ancient ices and dust turning in sunlight. Vents open and close as heat prowls across its surface. Grains of different sizes leave with different speeds. The coma around it is a cloud with 1,000 currents. Still look at the sequence, and you can feel the story: a sunward spray fading, an anti-solar stream strengthening, a deliberate-looking reversal told in light alone. You might suspect a trick of perspective. Astronomy is full of such tricks. Our planet moves, the object moves, the geometry breathes from night to night. Dust can trace the orbital plane, and for a moment line up to look like it points forward. We call that an anti-tail too, born not of intention but of projection, like the way Mars once seemed to back up in the sky until we learned to sit in the right frame of reference. So the teams do the sober thing. They lay down vectors, sun here, Earth there, comet's path sketched like a fine wire through space. They map phase angles and scattering angles. They correct for parallax and projection. They compare July's geometry to September's like a jeweler comparing facets. After those corrections, the reversal remains. Whatever we're seeing is not a two-dimensional lie, it is something in the object itself. Here the physics comes in quietly, like a teacher pulling up a chair. When a comet exhales, it pushes on itself. Gas rushes out, dust hitches a ride, momentum is conserved. Point that outflow toward the sun and the nucleus recoils sunward, breaking a little along its trajectory. Point it away from the sun, and you add a nudge to the outward swing, accelerating a little as it loops past perihelion. If you flip the dominant direction of jets, you should in principle feel that flip in the path, a measurable deviation from the clean curve gravity alone would carve. It's the same thought that turned fireworks into rockets and rockets into spacecraft. The sky listens to pushes and pulls. So the astronomers look for the fingerprint of push. They feed positions into orbital solvers, nights, weeks, months of astrometry, each measurement a bead on a thread. The solutions come back clean. Within the soft fuzz of uncertainty that always surrounds distant things, 3 Atlas is where Newton would put it, where Einstein would put it, no obvious non-gravitational acceleration singing above the noise. That absence is its own astonishment. You can see jets, you can see dust, you can see a reversal unfolding like a patient card trick under white gloves, but you cannot yet see a shove. 3 explanations volunteer themselves. Perhaps the nucleus is simply massive, so heavy that the recoil from its breathing barely registers. Perhaps the jets are many and exquisitely balance their thrust cancelling like a choir holding a chord. Or perhaps the third explanation, which is not truly an explanation but a placeholder for a future we don't yet speak, is playing at the edge of our vision that we are looking at behaviour, not accident. That last thought is not a claim, it is a caution, and science is careful with cautions. We have learned to delay our adjectives. Pulsars once suggested lighthouses of intention, until dense stars rotating at mad speeds blinked the mystery into clarity. Fast radio bursts wrote telegrams from other minds in the public imagination until the universe showed its own handwriting. If nature can imitate our designs, she will so well that we must prove ourselves wrong before we dare suggest we are right. Still, the images sit side by side like a before and after that refuses to serve a simple narrative. July's sunward glow looks like breaking thrust. September's anti-solar tail looks like forward thrust. Perihelion lies ahead like a test. The object is heading for its moment of maximum heat, where stresses find seams and seams find consequences. In that crucible, the physics of ice may account for everything: carbon dioxide that wakes early and blows bright, water ice that waits for nearer warmth and then speaks more strongly, grain sizes sorting themselves into different dances under light's steady push. It's the conservative story, and it is beautiful enough to want to be true. And yet the cadence of the reversal, the steadiness of the orbit, the way the light seems to tell a tale about choice. In the sleepless hours when the data are uploaded and the domes are closing and the coffee is gone, even the most disciplined minds allow themselves a minute for the old question: what would a maneuver look like if we didn't know how to name it? If a traveller from between the stars wanted to feel the curl of the sun and lean into it, brake then accelerate, what would we see from this far shore? We would see exactly this: a change in where the breath goes, a glow that turns its face, a silence in the path that says if there was a hand on the tiller it was steady. So we begin here not with certainty but with attention. An object crossed our thresholds and behaved as if it had changed its mind. Telescopes listened, humans lost sleep, the sky offered no apology. Jet inversion is not an answer. It is a prompt, a calm voice, at the edge of our understanding, asking whether we are ready to watch without presumption. Tonight you will lie down, but a part of you will remain at the window of the world, waiting for the next frame. The universe, as always, is about to finish a sentence. We will try, as always, not to interrupt. In July, the image looked like rebellion. In August, it looked like obedience. Between those two frames, barely 30 nights apart, lay a change that seemed to rewrite the grammar of sunlight itself. On one monitor in Hawaii, the July exposure from Hubble still glowed with its defiant posture, the plume leaning sunward as if some hidden force pushed back against the very radiation that should have been sweeping it away. Beside it, on another screen in La Palma, the August capture from the Nordic Optical Telescope showed the same visitor transformed its luminous thread, now trailing neatly away from the sun textbook behaviour, the kind astronomers could explain in their sleep. The universe had corrected itself, or pretended to. The hum in each control room was different but familiar. The quiet breathing of fans, the clicking relay of tracking motors, the muted rhythm of data packets arriving across fibre cables from the cold vacuum above. On those nights, observers weren't just collecting photons, they were collecting implications. Every few seconds, the sensors filled with another grain of ancient light, and each grain carried an opinion about what the object was doing, what laws it was obeying, and which ones it might be bending. Light tells stories by direction as much as by colour. When dust and gas stream from a comet, the solar wind and radiation pressure act like invisible fingers, pushing the smallest particles into an elegant arc opposite the sun. Large grains resist longer, tracing more curved paths. Gases glow in delicate halos. But 3 Atlas broke the choreography. The July image showed a plume toward the sun, an anti-tail that shouldn't have existed unless geometry was lying or physics was improvising. The simplest suspect was perspective. Earth moves roughly 30 kilometers each second around the Sun, the comet hundreds of thousands. Sometimes our lines of sight crisscross so that a normal backward-flowing tail projects forward on the sky, the same way two planes can seem to pass dangerously close even when they're miles apart. Astronomers have a name for that sleight of hand, the orbital plane crossing effect. If we happen to look edge-on through the dust sheet that trailed behind the object along its orbit, the path could appear to spike sunward. So they checked the geometry. They ran models not in poetry, but in coordinates. Right ascension, declination, heliocentric distance phase angle. Earth's position in July, its shift by mid-August, the comet's angle relative to both. The simulation painted vectors in space like a wire sculpture. If the anti-tail were illusion, the geometry would flip predictably. But even after adjusting for the shifting vantage, the reversal persisted. The plume that pointed toward the Sun in July did not simply fade. It rotated through weeks until it faced the opposite direction, as if the object itself had turned inside out. Outgassing drives that kind of behavior, yet in a quieter way. Beneath a comet's crust lie ices, carbon dioxide, carbon, monoxide, water, each with its own trigger temperature. When sunlight warms the surface, these frozen gases sublimate, escaping as vapor that drags dust along for the ride. If the object rotates, active regions blink on and off like vents on a spinning sprinkler. As the sun's angle changes, different ices wake and sleep. In principle, a flip could happen if one volatile shuts down while another takes over, each jetting from a different hemisphere. But the symmetry of 3I Atlas's change was unnerving. It wasn't chaotic, it was graceful. Back in the control room, scientists cross-checked exposure logs, camera temperatures, flat field calibrations. Nothing amiss. So the story migrated from equipment to nature. One researcher scribbled a note on a whiteboard, if not projection intrinsic. Underneath, someone else wrote, if intrinsic, then what flips a jet? Outside, the world went on airplanes, descending cities asleep, oceans repeating their tides, while a few dozen people in windowless rooms stared at two pictures separated by a month and a miracle. The hum of observatories at 3 a.m. is a kind of heartbeat for the species, the faint reminder that curiosity never sleeps evenly across the planet. Someone somewhere is always awake for the sky. The August data showed the glow fading sunward, the anti-tail thinning like smoke. By early September, the new tail, the proper tail, had lengthened into a fan of pale light stretching millions of kilometers behind the nucleus. Spectra revealed subtle changes, carbon dioxide emission, weakening water vapor, strengthening. The chemistry seemed to evolve with the geometry. That fit a natural narrative, yet the timing was suspiciously tidy, almost orchestrated. Imagine watching a dancer whose every motion follows music you can't yet hear. That's how the data felt, deliberate, timed, but silent about the score. Each measurement arrived hours late through the bottleneck of distance, like echoes from a conversation the universe was having with itself. The observers logged coordinates, brightness, color indices, then stepped outside to breathe air too thick for meaning. Above them, 3 Atlas continued its inward fall, neither confirming nor denying what they feared it might be. Science demands patience, but patience has a pulse. In private notebooks, scientists allow themselves small heresies. Could this be active control? Could this be composition boundary? Could this be? None of it makes the official papers. The words stay in pencil. Yet the mind can't unsee what the eye records. By the end of August, the global network of telescopes agreed the direction of emission had changed by nearly 180 degrees. No known projection could account for the magnitude. Something inside the nucleus or on it had shifted. Whether by thermal physics or by choice, a force had reversed the flow of matter itself. In La Palma, the astronomers closed the dome one night just before dawn. The air smelled faintly of salt from the Atlantic below. On the control screen, the final image of the session lingered, its data bar crawling toward completion. One of them whispered not as a theory, but as a prayer of sorts. It turned. Out there, where sunlight fades to black, the object kept moving as if it had never heard the words. Light, for all its obedience to equations, had just done something that felt like art. And the world once again had to learn how to look. In the mechanics of heaven, nothing moves without consequence. A push here is a pull there. Every exhale in space has its echo written somewhere in motion. That is the first law a young astronomer learns, and the hardest one to unlearn. Momentum is a promise. What sets a thing in motion keeps it there, unless something dares to interfere. So when 3i Atlas appeared to flip the direction of its jets, venting gas first toward the sun and then away from it, our equations demanded a reaction. There should have been a twitch in its path a tiny deviation from the track gravity alone would dictate, but there wasn't. The comet broke the rhythm of force without missing a step. To understand why that is unsettling, imagine holding a garden hose. When water rushes out, your hand feels a gentle shove in the opposite direction. The harder the spray, the stronger the recoil. It's Newton's third law, the one that says for every action there is an equal and opposite reaction. Rockets rely on it. So do comets. The vaporized gases blasting from their surfaces act as miniature thrusters. If the jets aim sunward, the recoil slows the comet ever so slightly. If they aim outward, the recoil adds speed. Even small outgassing can alter orbits enough that astronomers must include non-gravitational parameters in their models to predict where a comet will be months later. Most do this without complaint. They are ice that breathes, and therefore drifts. But 3i Atlas doesn't drift. It glides with unnerving precision as if the sun alone were holding the leash. Observatories from Hawaii to Chile fed its coordinates into orbit solvers. The residuals, the tiny differences between predicted and actual positions, fell within the noise floor of measurement error. A perfect passenger of gravity. That would be unremarkable if it weren't also actively shedding millions of tons of material. The comet was exhaling but not budging. Think of how different that is from our own machines. When a spacecraft performs a burn, every gram of expelled propellant counts. The Apollo service module, the Voyager probes, the Perseverance lander all obeyed the same rule. A brief thrust and trajectories bent in measurable arcs. In mission control, you could plot the correction on a screen, a kink in the line, a proof that chemistry had translated into motion. Even microthrusters on satellites' ions, whispering out at tens of kilometers per second, leave fingerprints in orbital data. Yet here was an object the size of a small mountain, venting continuously for months, leaving no sign of recoil. Two possibilities tame the paradox, at least on paper. One, the comet is so massive that its momentum dwarfs the push from its jets. Imagine trying to move a cathedral with a breath. The mass estimate, billions of tons, would make the recoil effectively invisible at our resolution. Two, the jets are balanced, firing from many regions in near-perfect symmetry, their thrusts cancelling like a choir holding a note, so even that the air itself seems still. Both explanations are possible, and both ask for an improbable level of coincidence. If symmetry is the key, then 3i Atlas is a masterpiece of balance. It would mean that as sunlight awakens one vent on the sunward side, another on the night side answers in kind, equalizing every push with a pull. Comets are not known for such grace. They are lopsided creatures, irregular as stones spinning erratically. Their activity flickers as they rotate, jets sputtering on and off with every sunrise over their terrain. Symmetry in nature is rare and fleeting. If mass is the key, then we face a different astonishment. The heavier the body, the slower it should respond to heating. A nucleus tens of billions of tons thick would store heat like an oven, its surface boiling while its heart remains frozen. That kind of thermal inertia could delay reactions, making outgassing appear self-regulated. Yet the same bulk would have endured cosmic radiation for eons, weathered interstellar dust, and still carried volatile ices capable of such vigorous activity. A paradox nested in a paradox, too big to move, yet too lively to stay still. This is why the reversal matters. It is not merely about direction. It's about coherence. The comet's body seems to act, but its path does not respond. The push and the motion are decoupled like a dancer whose gestures no longer align with the music. Physics can accommodate strangeness, but not contradictions. Somewhere in the equations, a term is missing or a new one waits to be written. Astronomers ran through their analogies, reaching for comfort. Could it be like a spacecraft performing a mid-course burn but compensating instantly, thrusting on one side and then on the other, so the net momentum change is near zero? Could it be like a gyroscope where internal forces shift orientation without altering the overall trajectory? Each comparison helped, and then fell short. Spacecraft execute such precision only under guidance. Comets do not take guidance, or so we believe. In that gap between belief and observation lies the whisper that keeps researchers awake. What if the unchanged orbit is the point a natural object fights against the sun's heat and wind, every jet a reflex? A controlled object might correct for those reflexes, maintaining its course, deliberately preserving an exact path like a satellite maintaining station. In the data, the two behaviors can look nearly identical. separated only by motive, and motive is not a measurable quantity. So we return to what we can measure: numbers, brightness, spectra vectors. The language of motion has no room for superstition, yet the feeling of wonder seeps through the margins. We know the physics of thrust, we invented it. We taught machines to do what comets do by accident expel matter for motion. And now we watch something doing the same, but cleaner, quieter, with no deviation at all. Somewhere beyond the orbit of Mars, Threatus's Atlas continues its glide, shedding its invisible breath, untouched by its own exhalations. It has become a mirror for our equations, reflecting not what they tell us, but what they leave unsaid. Momentum should change the path. The path hasn't changed. Between those two truths lies the puzzle, and perhaps the lesson, that the universe, when it wishes to test our certainty, does not break our laws, it obeys them too perfectly. The data keep arriving in the small hours, humming through cables into rooms lit by single monitors. Scientists compare timestamps, cross-calibrate instruments, and find again that the object is exactly where gravity said it would be. Outside, the wind stirs, leaves a smaller echo of cosmic breath. We have spent centuries learning how to measure motion. Now the universe has handed us something that moves without moving at all. And in that stillness we hear the faint question beneath all the numbers: what does it mean in a universe built on reaction to act and leave no trace? Numbers don't shout. They whisper in columns of decimals and slopes that barely bend in signals so faint that only patience can hear them. The story of Thri Atlas in late summer 2025 was not a spectacle of light, but a murmuring of data, flux readings, emission lines, brightness curves. Behind each point was a fragment of mass leaving the comet vapor dust and something like meaning. Between July and October, observers calculated that more than 2 million metric tons of material had streamed off the nucleus. 2 million tons, the weight of 3 Empire State Buildings dissolving into sunlight. On the screen, this evaporation looked tranquil, a soft brightening in the coma. But in physics, it was a storm, a furious exhale of molecules. Each one carried momentum. Each one should have nudged the nucleus. Each one should have whispered a change into the orbit. But when the numbers came back, the orbit hadn't budged. That was the first whisper that something didn't add up. Astronomers quantified the impossible the way they always do, through ratios and residuals. Measure the rate of gas flow, multiply by its velocity, divide by the mass of the nucleus, and you get acceleration. Newton's third law rendered in algebra. The thrust from those 2 million tons should have produced a slight but measurable deviation, a ripple in the predicted track. Telescopes charted positions night after night looking for it. Nothing. The comet's trajectory fit the purely gravitational curve like a bead sliding along a wire. It was as though the object were bleeding mass but not motion-shedding weight while gliding through space as if on rails. In that steadiness there was something serene, almost reverent, like the hush that follows a long breath in a cathedral. Motion without recoil, action without echo. The universe balanced on a knife edge, pretending not to tremble. To reconcile the silence, astronomers reached for scale. Maybe the comet was simply immense. If its nucleus were tens of billions of tons, then even a hurricane of escaping vapor would be a whisper against its inertia. Imagine tossing a pebble from a glacier. The glacier doesn't flinch. That interpretation painted Thri Atlas as a monument, a city-sized block of ice and rock, carved by interstellar ages dense enough to carry its own gravity like armor. But another interpretation lingered in the margins, harder to quantify and harder to ignore. If the object wasn't massive enough to hide its recoil, perhaps the recoil was being cancelled not by accident, but by control. The idea divided the room not along lines of belief, but of temperament. Some saw elegance in the heavy mass explanation, a natural symmetry, a comet so perfectly balanced that its emissions averaged out to zero acceleration. Others saw a choreography too precise to trust a coincidence. In their notebooks appeared tentative words like active compensation, stable thrust vector, phrases more at home in a spacecraft manual than in a comet report. No one claimed intent outright, not yet, but the tension had begun. On one side, gravity's simplicity, a giant object so heavy that its breathing made no difference. On the other, a whisper of engineering jets modulated with surgical care, keeping the trajectory exact. Both options fit the data. Both were improbable. The numbers deepened their paradox with each recalculation. Using brightness as a proxy for mass loss, teams estimated the thrust force, the product of exhaust speed, and expelled mass per second. The figures implied tens of thousands of newtons at times equivalent to several rocket engines firing continuously. Yet when divided by the inferred mass of the nucleus, the resulting acceleration was less than 1/millionth of a meter per second, squared smaller than the rounding error in most orbital measurements. The universe was performing high-energy physics with the poise of a heartbeat. One researcher likened it to a mountain sighing. Another, more poetic, called it the illusion of movement painted on still water. What united them was unease. In celestial mechanics, balance is rare. In nature, exact balance is almost forbidden. Systems seek equilibrium only to fall away from it. Here was equilibrium sustained flawless, indifferent to perturbation, a comet behaving like a machine built to suppress noise. The calculations turned philosophical. If mass loss and momentum were balancing so precisely what principle governed that harmony, was it coincidence, a happy accident of geometry, spin and solar heating, or was it a form of cosmic fine-tuning, an alignment so exact it felt authored? Scientists hate that word, but it fits the sensation, that sense of watching the universe thread a needle no one could see. In the quiet hours after the data runs, researchers stared at plots that should have been messy but weren't. The line of residuals lay flat, too flat. It looked like the sound of nothing silence rendered in mathematics. They reminded themselves extraordinary calm doesn't mean conspiracy. Comets can surprise, outgassing can be symmetrical, noise can hide signals, but still the question stayed like static under the music. How could an object lose so much so fast and remain so motionless? In physics, silence is never the absence of sound. It's the balance of all sounds. Every push meeting its pull, every note finding its opposite. That was the whisper of 3 Atlas and arithmetic perfection that felt almost deliberate. The cosmos does not explain its miracles. It only repeats them until we learn to listen correctly. For now, the listening continues. 2 million tons gone, no acceleration found, no certainty earned. The object sails onward, trailing a filament of dust as fine as breath, keeping its perfect poise in a sea of invisible forces. And beneath the calm hum of the instruments, humanity leans closer to its screens, trying to tell whether it's hearing the universe's quiet precision, or the muffled heartbeat of something that knows how to hide. When scientists talk about billions of tons, the mind drifts toward abstraction. A number that large becomes air too big to imagine, too smooth to touch. So let's slow it down, make it solid again. Picture an iceberg larger than Manhattan, its mass folded from frozen gases and black rock drifting in a sea of sunlight. If you could place 3i Atlas beside Earth, its nucleus somewhere between 2 and 5 kilometers across would rise higher than most mountains, a moving island of night that reflects only a few % of the light that touches it. You could fit whole cities inside its volume and still have room for their shadows. That is what astronomers mean when they estimate 30 billion metric tons of mass, a worldlet quiet and unclaimed, travelling faster than any storm on Earth. And yet we have never seen it directly. It's too far, too faint, too small to resolve into shape. All we have is light sunlight scattered, absorbed and re-emitted by dust and ice across hundreds of millions of kilometers. From that dim glow, scientists extract weight, temperature, texture. It's a strange alchemy, turning photons into matter. Brightness tells us how much sunlight the object reflects. Color tells us what the surface is made of. A pale blue hue suggests fresh ice. A reddish tone hints at carbon-rich dust baked by cosmic rays. By measuring how the brightness changes with distance from the sun, astronomers infer how volatile the surface materials are, how easily they sublimate, how vigorously they jet. From these changes, they build a model of the nucleus, not as a photograph, but as a probability map, a sculpture made of equations. The numbers whisper an albedo around 4% darker than asphalt, a diameter of a few kilometers, a rotation period that may stretch to dozens of hours, though no one is certain. A bulk density somewhere near 600 kilograms per cubic meter, light as pumice, porous as snow. Multiply those figures and you get the mass 30 billion tons, give or take a factor of 2. Enough to outweigh Mount Everest if you could lift the mountain off its roots and set it in the void. These are not guesses, they are deductions drawn from the faintest traces of light. When a telescope collects a comet's glow, it doesn't record a solid beam, it records photons arriving one by one, random like raindrops on metal. Each photon carries a color, and the pattern of those colors, the spectrum, reveals chemical fingerprints. Hydrogen, oxygen, carbon monoxide dust grains scattering blue light more than red. The trick is patience. Gather enough photons and the noise resolves into structure, the way a long exposure reveals stars invisible to the naked eye. It's easy to forget that the object itself never knows it's being watched. It travels through space as it always has, rotating, gently leaking sunlight into the dark. But for us, its faint reflection becomes a bridge across the impossible distance. Measuring its brightness is like listening for an echo in a canyon where the original sound has long since faded. What returns tells you something about the shape of the walls, the air between, and your own position within it. When we say 3i Atlas lost 2 million tons of material, that too comes from light. The coma, the hazy envelope surrounding the nucleus, scatters sunlight in proportion to the number and size of particles within it. Track how that brightness evolves from night to night, correct for distance and phase angle, and you can calculate how much dust and gas must be leaving the nucleus to sustain the glow. Over months, that adds up to millions of tons matter transformed into light, then translated back into matter again through mathematics. If this sounds circular, it is beautifully so. Astronomy has always been a discipline of indirect knowing. We never touch the things we study. We infer their presence from the light that finds us. Every comet, every galaxy, every possible alien shore, known by its brightness, its color, its rhythm in time. We live by reflection. That reflection carries a spiritual rhythm as well. Imagine the comet's surface as a mosaic of ices, carbon dioxide, methane, ammonia, water. As it turns toward the sun, each patch sings at its own temperature, releasing vapor that joins the coma like breath joining air. The nucleus darkens as it sheds its most volatile layers, revealing older, heavier materials beneath an autobiography written in melting ink. The process is violent in scale but delicate in effect, like frost evaporating from a window pane. From Earth, all we see is a slight change in brightness, a flicker in the scatter of sunlight. These measurements teach humility. We think of telescopes as powerful, but their power is subtle to interpret the quiet, not to command it. The astronomers tracking 3i Atlas spend nights aligning mirrors, adjusting filters, waiting for clear skies. When a frame finally comes through, it looks like noise, a handful of stars and one faint smear. Yet within that smear lies the architecture of a mountain moving through the void. That mountain is still losing mass, still unperturbed, still sliding along its predetermined arc. If it were to strike Earth, it could vaporize continents, but it won't. It isn't coming for us. It is simply passing by, ancient and aloof. Our task is to learn what it can teach before it fades into the long silence between the stars. To translate its scale into human terms is to remind ourselves how small we are and how much attention can reveal. 30 billion tons, 2 million tons lost no measurable acceleration. These are not contradictions but chords in a single composition. A cosmic instrument tuned so precisely that even its roar sounds like stillness. Through brightness, through color, through the patience of those who refuse to sleep, we hear it an iceberg the size of a city melting into equations whispering across the abyss. This is how large nothing can be, and how quietly it moves. Deep inside 3 Atlas, far beneath the dust-dark crust that faces the sun, lies a library of ice pages layered across cosmic ages, each one a record of where this traveler has been. Out here in the cold, between stars, silence is structure. Every molecule of frozen gas has waited motionless for its turn to speak again in vapor. Now, as sunlight touches the surface for the first time in perhaps a million years, that library begins to read itself aloud. Sublimation is the physics of disappearance, a solid turning straight to gas without ever melting. On Earth, you can see it in the faint wisp rising from dry ice, or in the way laundry hung outside on a winter day slowly vanishes into air. In the deep freeze of space, sublimation is the pulse of comets. When solar heat penetrates the upper layers, it wakes molecules of carbon dioxide and carbon monoxide gases that evaporate easily even in the cold. They burst from tiny vents and fractures, dragging grains of dust with them, creating jets that glitter in sunlight. The comet's surface becomes a shifting skin, equal parts eruption and erosion. Carbon dioxide ice, the most volatile of these ices, begins to vaporize long before the comet reaches the orbit of Jupiter. Its molecules are impatient. Even at temperatures hundreds of degrees below water's freezing point, they can escape their crystalline cages, forming invisible geysers that leap into space. water ice heavier and more loyal to cold waits until the comet ventures closer to the Sun. Only when the surface warms past roughly the 70 degrees do the first molecules break free, joining the carbon dioxide plume and giving the coma its ghostly blue-white glow. It's as though the comet holds two breaths in its lungs, one shallow, one deep. The first exhale of carbon dioxide is crisp and early a whisper in the outer darkness. The second of water is warmer and longer, a sigh released as the Sun climbs higher in the sky. The transition between them is not abrupt, but layered like turning pages in a frozen book. Each page is a stratum of chemistry, ancient interstellar frost near the surface, younger solar system ice below trapped gases, organic dust. As sunlight digs deeper, it peels back those chapters in order reading the story of the object's formation through vapor. Imagine a glacier under a slow sunrise. At first only the peaks glint, then the ice begins to sweat, to sparkle, to trickle. Under the topmost crust, microcavities fill with gas until the pressure shatters the seal. A puff of jet, a brief storm of dust, and a new crater forms, venting energy like breath from a sleeping giant. On 3i Atlas, each of these tiny eruptions releases more material into space, feeding the tail that stretches for millions of kilometers. Yet from our distant vantage it looks serene, a ribbon of light drawn by invisible hands. To the scientists modeling this process, the physics feels intimate. Heat conducts inward, temperature gradients steepen, molecular bonds loosen in a cascade of thermodynamic poetry. Beneath a few meters of crust, the balance between pressure and cohesion can hold for centuries until a fraction of a degree tips it into eruption. The equations describing this are simple latent heat of sublimation gas, constant molecular weight, but their consequences are unpredictable. A single crack can change the pattern of jets, shifting the center of mass just enough to alter rotation. Over time, the comet's spin wobbles, its day lengthens or shortens, and new regions face the Sun. Each cycle reshapes the map of active vents, turning the nucleus into a living landscape. When carbon dioxide runs out near the surface, the baton passes to water. The heavier ice melts into vapor more reluctantly, but when it does, the outflow grows denser and more visible. Dust grains trapped in the upper layers of ice are freed, scattering sunlight into the familiar pale tail. As the comet approaches perihelion, even deeper compounds ammonia-methane trace organics may join the chorus. Each molecule sings its own spectral note, identifiable by the light it absorbs and emits. In spectroscopy, those notes appear as faint colored lines. In poetry, they sound like memory. The temperature difference between the sunlit and shadowed sides can reach hundreds of degrees. On the night side, ice is recondensed, sealing vents that will reopen the next rotation. The whole body inhales and exhales, once every turn a frozen respiration on a cosmic scale. Some astronomers call it the comet's heartbeat. Others prefer to think of it as an orchestra, each jet a separate instrument rising and falling with distance from the Sun, the melody written in gas and dust. 3 Atlas, being an interstellar object, carries a more exotic composition than our homegrown comets. Its ices were probably forged in the molecular clouds between stars under conditions so cold that even nitrogen froze. Some of its atoms may have been born in supernovae dusted across the galaxy, before coalescing into this single lump of chemistry. Every time sunlight strikes it, those ancient atoms resume a journey interrupted for eons, drifting once again into open space. We watch this process from hundreds of millions of kilometers away, translating its invisible size into numbers on a chart. Each increase in brightness, each shift in spectral color marks another layer peeled from the nucleus, another sentence erased from that frozen autobiography. Over weeks, the library inside 3i Atlas grows thinner, page by page, until one day nothing remains, but the binding a dark core, exhausted, tumbling quietly away. Yet within that vanishing lies its beauty. Sublimation is decay that writes light. It is destruction that informs. When the ice evaporates, it carries stories older than our sun into the open sky, scattering them like dust over our telescopes. And as those molecules rush outward at hundreds of meters per second, the comet's mass diminishes but its meaning expands. So when we say the ice inside, we are speaking not of coldness but of time itself, time stored as matter released as breath. A glacier breathing under sunlight, a frozen book unbinding, a memory turning back into motion. In the end, that is all 3i Atlas may be an ancient lung of the galaxy, exhaling the story of where it came from, and reminding us that even the coldest hearts eventually learn how to sing. As the days shorten and a three-eye atlas drifts ever closer to the sun, the object begins to molt. What was once a ghost of frozen carbon dioxide becomes something warmer, more restless, almost alive. To the telescopes that never sleep, this transformation looks like a shift in colour, a rearranging of brightness. To the imagination, it's a metamorphosis, the old ice giving way to the new, the traveller changing its face before our eyes. Abraham Loeb and Andrew Keto gave this transition a map, a scientific shape. In their model, the reversal of the comet's jet, the strange act that made Three-Eye Atlas seem to change its mind, was not a feat of control but of chemistry. The outermost layer of the nucleus they propose was laced with carbon dioxide and carbon monoxide ices. These are volatile, delicate things. They awaken early singing their vapour songs far from the sun. When sunlight first brushed the comet at a distance of 4 astronomical units beyond the orbit of Mars, the CO2 began to flee, expanding violently through pores and fissures. Those jets light and quick shot dust sunward and gave birth to the July image, the comet glowing toward the light, a defiant inward-pointing plume. But then as the comet fell inward, a threshold was crossed. The carbon dioxide near the surface ran out, its reserves spent. The layer beneath, richer in water ice, tougher, slower to stir, came into play. Water waits. It requires more heat to turn to vapour, more intimacy with the sun. Only when the comet reached roughly 2 astronomical units did the water begin to move. At that moment, the pattern inverted. The new jets were heavier laden with coarser dust grains, their momentum slower, but their persistence longer. Under radiation pressure, that heavier material curved outward away from the sun. The anti-tail faded, the proper tail bloomed. The glow that had once leaned inward now stretched behind like a veil of transformation. To Loeb and Keto, it was a simple sequence of chemical awakenings, a changing of guards between ices. The carbon dioxide phase was an overture, the water phase a crescendo. What the world saw as reversal was in fact renewal. But beneath the equations lies something gentler, more human. Every traveller changes under heat. The closer we come to our own stars, the more our layers evaporate, the more we reveal of what lies beneath. Three-Eye Atlas was no different. The heat that threatened to break it also revealed it. For millions of years it had drifted through interstellar dark, its carbon dioxide skin shielding its deeper self. Now, under solar light, it shed that ancient armour, and for the first time in aeons, the water inside water that may have predated Earth's oceans found freedom. Imagine standing on its surface in that moment, though surface is too strong a word for a place that is mostly void and vapour. The ground would tremble with invisible tremors as sunlight cracked through the crust. Beneath your boots, ices would hiss and vanish, carving tunnels that vented skyward like breath. The sun would rise and set every few hours as the comet spun each dawn, awakening a new patch of frozen terrain. In one rotation, you might see the last of the carbon dioxide plumes sputter out like dying candles, while new geysers of water vapour ignited on the opposite horizon. It would feel less like death than like molting an ancient creature shedding its skin for another chapter of its voyage. From Earth, this process unfolded in silence. Spectra captured from La Palma and Mauna Kea began to show the change. CO2 emission lines weakening H2O features, brightening dust grains growing larger, more reflective. The ratio of gas to dust altered too, implying that more solid material was being lifted. The comet was transitioning from ghost to body, from faint haze to full plume. What July's telescope saw as defiance had become by September surrender, and in that surrender a kind of grace. Loeb and Keto's model framed the event not as miracle but as thermodynamics. Yet in the quiet hours of analysis, even they acknowledged the poetry. A body from another star system had travelled light years carrying its layered heart intact, only to unwrap itself in sunlight, revealing each chemistry in turn like petals opening. To the physicist, it was a demonstration of how volatile ices stratify and respond to heat gradients. To anyone with a pulse, it was metamorphosis, the transformation of one kind of being into another through fire. The metaphor held. The comet's journey inward mirrored a kind of awakening. Its early phase, cold reactive carbon bright, was the instinctive life of survival burning through the easiest fuel. Its later phase, slower, denser enduring, was maturity built on patience and balance. Even the jet reversal, once scandalous, now read like a natural evolution, the creature turning its face from curiosity to contentment, from searching to continuation. In their papers, Loeb and Keto expressed it in graphs and ratios, sublimation coefficients, thermal conductivities, activation distances. But behind the numbers was a rhythm, a cosmic metabolism as old as starlight. When the comet passed through 3 astronomical units, the CO2 dominated. At 2, the ices mixed. Near 1.5, water ruled. At perihelion, the sun would turn the outer shell into vapor, leaving a smaller, darker core to journey outward again, wrapped in the remnants of its own shedding. Observers called it the Great Transition. To some, it proved that all mysteries can be tamed by chemistry. To others, it showed that understanding and wonder can coexist, that to explain a thing does not mean to unmake its beauty. 3i Atlas was not breaking laws. It was writing them in a more elegant script, and somewhere between the numbers and the night sky, between CO2's impatience and water's endurance, the comet's personality changed not from inanimate to alive, but from simple to layered, from static to evolving. A worldlet learning to breathe in sunlight, turning its cold mathematics into warmth. From a distance, it looked like a reversal. Up close, it was revelation. The object had not defied the sun, it had remembered it. By the time September waned, the anti-tail was gone, the true tail blazing behind, and 3i Atlas was on course for its moment of trial. What remained was to see whether its transformation would hold, or whether the fire of perihelion would burn through even this new identity. The Great Transition was not only the comet's, it was ours, the shift from asking what if it's impossible to wondering, what if it's natural and nature is more miraculous than we knew. They called it the verification window. Those tense luminous weeks between mid-September and the first days of October, when every instrument on Earth and in orbit turned its mirrors toward 3i Atlas. The comet had completed its Great Transition. Now came the test. If Loeb and Keto were right, the chemistry of the jets should reveal a clean handover from carbon dioxide to water vapor, from quick invisible gas to heavier reflective dust. In the language of science, it was time for confirmation. In the language of night watchers, it was time for staying awake. The quiet orchestra of verification. Spectroscopy came first. Each element and molecule has its own voice, a set of wavelengths it absorbs or emits bright lines on a dark rainbow. Carbon dioxide sings in the infrared water in a shimmering band near 3 microns. Point the right instrument at the comet and those songs separate like chords on a piano. The observers knew the score by heart if the CO2 lines dimmed, while H2O lines brightened. As the comet neared the sun, the compositional transition model would stand. So they listened in Chile and Hawaii and the Canary Islands, converting photons into soundless music. A graduate student in Mauna Kea's control room wrote in her notebook at 3:47 a.m, "Spectrum clean, CO2 almost gone, waterline rising, the object is becoming itself." Later, she would delete that last sentence before submitting her log. Astronomers are careful not to sound enchanted even when they are. At the Very Large Telescope in Paranal, Chile, the same pattern appeared. The CO2 feature at 4.3 microns, once strong, was fading. The 2.7 micron H2O line grew day by day. Each data run confirmed what chemistry had predicted. But numbers alone weren't enough. To complete the story, they needed to know what the dust was doing. The study of grains. When gas escapes from the surface, it carries dust grains of different sizes. Small grains scatter. Blue light, large grains scatter red. By measuring how the comet's color changes with time, scientists estimate the grain distribution, the texture of the coma. In July 30, Atlas looked bluish, dominated by fine CO2-driven dust. By September, the hue had reddened slightly, evidence that heavier water-entrained grains were taking over. It was the comet's complexion changing with age. At the Nordic Optical Telescope, the night shift stretched endlessly. Inside the dome, the air smelled of oil and cold metal. A kettle hissed beside a tangle of cables. 2 researchers traded turns at the console marking exposure numbers in pencil. Outside, the Atlantic crashed unseen against the rocks below the Sound, arriving half a second late. The graduate student on duty looked up between frames and whispered, "She's turning redder," as if the comet might hear. Polarization, light's secret, tilt. A third clue lay in the polarization of light, the direction of its electric field after bouncing off dust. When sunlight strikes fine particles, the scattered light becomes polarized at specific angles, revealing the grain's size and composition. It is like reading the brushstroke of a painter by the direction of the bristles. In July, polarization patterns suggested clouds of tiny grains, chaotic and uniform. By late September, the degree of polarization increased to larger, more irregular particles reflecting light like powdered glass. That too fit the transition model, the shift from the quick breath of CO2 jets to the slow exhalation of water vapor carrying coarser dust, human time versus cosmic time. Each of these tests required nights of stillness and repetition. The comet moved, but not impatiently. The sky spun overhead in perfect rhythm. Human lives compressed into schedules and deadlines had to stretch to meet it. Coffee cups multiplied, eyes reddened, conversations dwindled into shorthand line 2.7, good seeing 0.8, arcsec continue run. In the small hours when fatigue blurred the numbers on screens, some found themselves watching the live feed not for data but for beauty, a single pixel-wide smear drifting across a field of stars that had not moved in 10,000 years. The object was changing, yes, but at a pace that mocked urgency. The observers began to sync themselves to cosmic time. They learned to nap in 90-minute intervals between exposures to eat quietly, while scripts ran to measure progress not in hours, but in revolutions of the comet around its axis. Each dawn felt like a page turn in a very slow book, the verdict emerging. By early October, the evidence converged. Spectra water vapor dominant, colors redder, dustier, polarization higher, consistent with larger grains. No sign of artificial reflection, no spectral anomalies beyond known chemistry. If there was mystery left, it was not mechanical but philosophical. Loeb and Keto's model held the comet's strange behavior was a natural transition, not a maneuver. Yet even as the equations clicked neatly into place, the awe did not fade. To watch a worldlet remake itself under sunlight was still miraculous, even when perfectly explained. In the nightly log from Paranal dated October 2nd, an exhausted observer typed one final line before closing the dome. Transition confirmed. Object stable. Still beautiful. That's how science often ends, not with revelation, but with quiet affirmation that nature's script was written correctly after all. Still, as the last images of the night uploaded, she lingered by the console eyes on the faint tail stretching beyond the frame. The comet had kept its secrets for 1 billion years. It could afford to share them slowly. Outside, the desert wind carried fine grains of sand across the observatory walls, Earth's own reminder that transformation is everywhere, even here. The data would be analysed, graphed, published. But the memory that would stay was simpler. The rhythm of patience against cosmic time, the hum of instruments, and the gentle awareness that in seeking proof they had witnessed poetry. And above them, Nost Atlas kept gliding, no longer rebelling, no longer explained away, simply continuing its quiet metamorphosis, under the watchful eyes of a sleepless species learning how to listen. At first, the engineered probe idea lived only in margins, pencil questions beside clean graphs, a passing what-if shared in hallways after conferences when the projectors were off and voices could drop to human pitch. The data fit the natural model, yet something about 3 Atlas still felt rehearsed. The timing of the jet reversal, the exquisite balance of forces, the orbit that refused to wobble, too symmetrical, too composed. A few scientists, unwilling to discard wonder, began to ask a different kind of question. What if this is control, not coincidence? They didn't mean science fiction. They meant engineering guidance, thrust modulation, feedback. The same principles that steer spacecraft through interplanetary arcs could in theory sculpt a comet's behavior. In the quiet language of technical memos, they speculated about active surface stabilization or autonomous energy redistribution. None claimed proof. They only noticed echoes, familiar signatures of precision in a place where randomness usually reigns. The resemblance to design wasn't new in astronomy. Half a century earlier in 1967, a young graduate student named Jocelyn Bell noticed a radio pulse repeating every 1.3 seconds. Its regularity was so perfect that her team jokingly labelled the source LGM-1 Little Green Men. The mystery resolved soon enough, a rapidly spinning neutron star, a pulsar, sweeping a lighthouse beam across Earth with mechanical grace. Nature, it turned out, could outperform our engineers in precision. Then again, in the 2000s, the sky produced fast radio burst, millisecond flashes of energy that appeared out of nowhere. For years, they teased SETI researchers. The signals were so sharp they could have been digital pings. Only later did we learn that collapsing magnetic fields in distant galaxies could shout as neatly as any transmitter. The pattern repeated machine-like behavior emerging from physical law design without designer. So when 3I Atlas pirouetted with such balance, reversing jets, maintaining orbit history offered caution. We had been fooled before by the universe's competence. And yet, the resemblance was hard to ignore. The object did not simply vent, it regulated. It did not tumble chaotically. It rotated with steadiness that seemed servo-controlled. Its changes came in phases as though following a schedule. To a few restless minds, it looked less like geology and more like governance. Measured discussions arose on late-night video calls between observatories. Screens glowed with spreadsheets and weary faces. Suppose one physicist said that an interstellar probe disguised itself as debris. Wouldn't it need a low albedo to avoid detection? A volatile layer for course corrections, another replied, that's storytelling, not modelling. But even as she said it, she smiled the way someone smiles when imagination edges close to mathematics. The hypothesis carried no evidence, only pattern recognition. Yet pattern recognition is where all hypotheses begin. The oddity was not that scientists entertained the thought, it was that the data left room for it. A comet that loses millions of tons without measurable recoil feels deliberate the way a magician's silence makes you suspect a trick. Some argued that nature's balance is enough explanation. Others felt balance that perfect needs a balancing hand. The journals stayed cautious, peer review demands restraint. The word probe appeared only in online forums and speculative essays. Still, a few respected voices noted that if another civilization had ever seeded self-replicating machines, von Neumann probes across the galaxy, we might expect them to camouflage as ordinary comets. Ice and dust make excellent armor. A damaged or dormant probe half melted by time might look exactly like 3 Atlas. To the general public, such musings sounded extravagant. To scientists, they were exercises in humility. The goal wasn't to claim alien engineering, but to remind ourselves that the universe is vast enough to contain both order and accident, and that our instruments can't yet tell them apart. The boundary between artifact and natural law may be thinner than we think. It helps to remember how often nature invents our inventions first. Bees build hexagons before mathematicians prove them efficient. Supernovae forge heavy elements in blast furnaces long before we dream of reactors. Even the brain, an electrical network tuned by feedback, mirrors the algorithms of computers that came billions of years later. Design and emergence are twins wearing each other's clothes. So the probe idea survives, not because it is likely, but because it is instructive. It asks, how would we tell the difference? What measurements could separate an intention from a coincidence? Could we detect encoded modulation in the dust jets? Could we find spectral lines out of place? Metals too, pure isotopes too even. Each speculative question sharpened the next experiment. Curiosity, not conviction, kept the discussion alive. As October progressed and the comet neared the sun, most evidence continued to support the natural model. Yet during one meeting, a researcher closed her presentation with a quiet slide. 2 images side by side. 3i Atlas in July, plume forward. 3i Atlas in August, plume reversed. Below them she wrote only 5 words. Sometimes symmetry is suspiciously kind. The room stayed silent for a moment. Not out of belief, but out of respect for a universe that keeps blurring the line between physics and intention, between accident and artistry. And perhaps that is the real lesson of 3i Atlas. Not that it is artificial, but that nature itself behaves as if it had read our blueprints and chosen to mimic them. We look up seeking mirrors of ourselves, and the cosmos obliges not with answers, but with echoes of design rendered in dust, sunlight, and silence. For the scientists who lost sleep to measure that silence, this resemblance was not embarrassment, it was grace. The sky once again had reminded them that wonder and rigour are not opposites. They are like the comet's twin tails, 2 expressions of the same motion. Somewhere beyond Mars, 3i's Atlas continued on its course, neither confirming nor denying, merely reflecting light in patterns that felt like thought. And we as always mistook that reflection for a face. By October, the rumour had outgrown the data. Online headlines spoke in capital letters, while the scientists who had actually watched the comet spoke in sighs. To them, 3i Atlas was no miracle, no messenger, no proof of design, only a patient question too large to be answered in one night. In science, such questions are common, and so are the temptations that come with them. The real challenge is not to believe too quickly, it is to stay curious without surrendering to the noise, the discipline of doubt. Every extraordinary claim begins the same way, with a whisper in the data, a blip that doesn't fit an image that looks a little too deliberate. But before wonder can bloom, the method must step in. First rule, repeat it. Second, check your instruments. Third, invite someone who doesn't already agree with you to look. The scientific method is not a ladder but a sieve. Most ideas fall through. Only those strong enough to survive skepticism earn the dignity of theory. That is why astronomers cultivate humility like a crop. They know that the sky loves to trick them. Atmospheric turbulence can forge phantom stars. Cosmic rays can mimic alien signals. Calibration errors can invent entire phenomena. Even honesty needs guarding because the eye wants to see meaning and the mind wants to keep it. So when faced with a puzzle as delicate as Three-Eye Atlas, the community's first instinct was not celebration but caution. Skepticism in this world is not cynicism. It is devotion, the daily practice of keeping the sacred separate from the seductive. Ghosts of past revelations. Astronomy's archives are filled with false alarms that once wore the crown of discovery. In 1879, William Huggins thought he had found oxygen on the moon's spectral lines, later proved to be Earth's own atmosphere. In 1929, a team in Berlin believed they had captured radio from Mars' an antenna fault. In 1967, the pulsar that blinked with perfect rhythm became LGM-1, before becoming just PSR B991+21. Even in 1977, when the WOW signal erupted from the Big Ear radio telescope, the burst seemed so precise that hearts stopped. Decades later, no pattern returned, and WOW remains a note pinned to the door of the unknown, exciting, unrepeatable, unresolved. Each of these moments shaped a culture of patience. Scientists learned that it is possible to be thrilled and wrong at the same time. They learned to love uncertainty, to make their peace with the unfinished. So when Three-Eye Atlas appeared to break, then accelerate, then defy recoil, the community reached for that muscle memory: measure twice, speculate once. The slow machinery of proof. Testing an extraordinary claim is less like hunting than gardening. You plant observations, water them with peer review, prune away bias, and wait through seasons of replication. If the anomaly survives 100 skeptical eyes, it graduates from curiosity to candidate. If not, it returns quietly to the compost of history, feeding future questions. For Three Atlas, that process was already underway. The same observatories that had thrilled at its reversal now sought to dissolve the romance into numbers. New data from JWST were compared against models from Keto's team. Radar echoes were cross-checked with photometry. The spectral ratios were reanalyzed for signs of silicon or titanium metals that might hint at fabrication. None appeared. Every test that could have cracked open an extraordinary claim instead deepened the ordinary one, and yet no one was disappointed. For scientists, a mystery explained is not a miracle lost, it's a miracle understood. Humility as compass skepticism, rightly practiced, is a form of respect. It assumes that the universe deserves accuracy. It refuses to flatten mystery into mythology. In the long arc of discovery, humility has saved more truth than certainty ever has. Darwin waited 20 years before publishing On the Origin of Species because he wanted the evidence to speak louder than his conviction. Einstein, who overturned Newton, spent decades refining equations that might have faltered under one wrong decimal. Even Galileo, defiant before inquisitors, paused to correct his own measurements of Jupiter's moons before declaring them worlds. This same humility hums through the modern observatories. It's there in the graduate student who rechecks calibration frames at dawn, in the senior astronomer who publishes not a headline but a correction, in the unglamorous patience of data reduction. They are not guarding belief. They are guarding accuracy, the only altar science truly keeps. The grace of not knowing. And so the engineered probe idea, for all its poetic allure, was folded gently back into the drawer of speculation. Not ridiculed, not erased, just set aside until evidence might someday return. That's how science honors its ghosts, by letting them rest until the data call them awake again. If history teaches anything, it is that truth arrives last walking slowly through a crowd of hopeful mistakes. Every false alarm refines the next real signal. Every disciplined doubt protects the next genuine wonder from being lost in noise. In the end, Three-Eye Atlas remained what it had been all along, a question. And that was enough. Because the point of watching the sky is not to prove ourselves right, but to be corrected by something larger, older, and infinitely patient. Each night the telescopes opened their shutters again, and the same ritual resumed: focus, measure, compare, doubt, repeat. Outside those domes, the world spun through its own chaos of news and sleep and speculation. Inside, amid the quiet clicks of tracking motors, a different rhythm held a kind of faith in slowness. For those who work with the stars, humility is not a virtue, it's oxygen. Without it, you cannot breathe the truth long enough to recognize it. So the scientists watched, measured, and waited, devout not to belief, but to evidence, while the object itself glided on, unbothered by our interpretations, and in that steady indifference there was a kind of mercy. The comet asked no faith, offered no revelation. It only shone, reminding us that the difference between skepticism and wonder is not distance, but honesty. Truth, after all, is never offended by doubt. It only asks that we look again tomorrow night. By mid-October 2025, the long arc of approach had steepened into a plunge. For 18 months, astronomers had watched 3i Atlas glide with distant poise, a ghost among the planets. Now, at last, it began to fall. The sun was pulling it homeward or toward judgment at more than 100,000 kilometers per hour. Each day, the light grew fiercer, the coma brighter, the interval between observations shorter. This was the countdown to fire the final sprint to perihelion on October 29, 2025, when the object would pass a mere 1.356 astronomical units from the Sun closer than Earth deep inside the furnace of space. The trial by heat. In the weeks before perihelion, the comet entered what engineers would call its thermal stress regime. Solar radiation at that distance pours down with nearly twice the intensity felt on Earth. For an interstellar traveller hardened in cold between the stars, it was like awakening inside a blast furnace. Surface ices of carbon dioxide and carbon monoxide would already have boiled away. Now even stubborn water ice began to sublimate, explosively venting geysers that could lift boulders. Each jet carried momentum miniature rockets firing in random directions. The nucleus shuddered. Internal pressure climbed as trapped gases sought escape through fractures that had lain dormant for eons. A wrong crack, a resonant vibration, and the worldlet could tear itself apart. Astronomers had seen it happen before. Comet Ikeya-Seki in 1965 brightened so fast before its solar graze that instruments saturated. Then it split into 3 pieces and survived only as a veil of the dust. Comet Lovejoy in 2011 passed even closer, skimmed the sun's corona, emerged trailing luminous ribbons, and disintegrated days later. To watch such trials is to feel both awe and pity, ice surrendering to light. 3i Atlas now approached the same ordeal, the observational gauntlet. Telescopes around the planet readied for a relay. The geometry was cruel. Near perihelion, the comet would lie close to the sun in the sky, visible only during narrow dawn and dusk windows when sunlight bled out of the horizon. Each observatory had minutes, not hours, before glare overwhelmed the detectors. On Mauna Kea, teams rehearsed twilight runs, scripting exposures second by second. In Chile, engineers recalibrated filters to protect optics from the solar edge. Even space telescopes faced limits. Hubble could not safely point within 50 degrees of the sun, and JWST's sun shield forbade riskier angles. Only solar-dedicated instruments, the European Space Agency's Solar Orbiter, NASA's SOHO, and the vigilant eyes of Stereo could keep watch continuously. For them, this was more than curiosity. It was a chance to witness interstellar material tested by the sun itself. Inside mission control rooms, countdown clocks multiplied. Scripts scrolled in columns: acquire target, expose, shift filter, repeat. Data pipelines were tuned for speed-raw photons streaming to servers in Maryland, Madrid, and Tokyo. Every hour, new frames arrived, tiny overexposed crescents against the blaze. Software subtracted glare, revealing the ghostly nucleus hurtling into dawn. The temperature curve. At 1.5 astronomical units, theoretical models predicted a surface temperature of roughly 260 Kelvin, warm enough to melt ammonia. By perihelion, it would exceed 330 Kelvin, hot enough for the first layers of silicates to dehydrate, releasing oxygen and metal ions. Some expected the coma to surge in brightness tenfold. Others warned that the object might fragment before they could measure it. If the nucleus held together, the spectacle would be brief, but magnificent jets, roaring tail lengthening to millions of kilometers, the dust reflecting sunlight into a fan visible even through the sun's halo. If it fractured, each shard would become a new experiment, a micro-world exposing its interior composition before fading into steam. In the labs, thermal stress models ran overnight. Graphs plotted internal temperature gradients, tensile strengths, spin rates. Would centrifugal forces exceed cohesion? Would vaporization occur uniformly or explosively? No one knew. A comet's endurance is written in randomness. porosity fractures, grains bonded by frost older than the solar system itself, racing the sun. Imagine it now a mountain of ice and rock 5 kilometers wide, turning slowly as it falls. Ahead, the sun expands until it fills half the black sky. Space vibrates with photons. The nucleus begins to boil, each venting plume, a scream of escaping molecules. The coma thickens into a shroud, reflecting the golden light in streaks of turquoise and white. To distant observers, the object seems to glow from within a lantern descending into the forge. Time dilates. The closer it gets, the faster it moves. By the final week, it travels 30 kilometers each second. Every frame from every telescope could be the last intact glimpse. There is poetry in the peril. For the scientists who have watched it since discovery, the approach feels personal, a year of sleepless nights condensed into hours of fate. When the data finally pour in, they will either capture a resurrection or an obituary. Either way, the meaning is immense, a story of endurance written in sunlight. The night before, October 28th, across 3 continents the observatories wait. In La Palma, clouds gather then clear. In Chile, wind stills. At Mauna Kea, the horizon glows faint orange. Somewhere beyond that glare, through Atlas begins its final descent. The watchers hold their breath, fingers hovering over record buttons, knowing that for the next 48 hours, the universe will decide whether this visitor leaves memory or debris. At perihelion distance, the comet will encounter light 800 times brighter than any it has ever known. It will face forces that no material born in interstellar cold was built to survive. But perhaps, like others before it, it will surprise us, fracture, yes, but not vanish, scatter itself into a new geometry bright enough to write one more chapter across the morning sky. And as the final night deepens, the instruments hum softly, their sensors already warming in anticipation. Somewhere in the data streams waiting to be decoded lies the next revelation, whether of endurance, destruction, or transformation. Because every perihelion is both a death and a beginning, and 3, Atlas racing toward the sun has become our mirror in that truth. Tomorrow, the fire. On October 3rd, 2025, 3 Atlas passed within 0.48 astronomical units of Mars, just 70 million kilometers a handshake by interplanetary standards. For Earth, the comet still shimmered as a faint arc at dawn. For Mars, it was a streak of light threading the thin orange sky, and orbiting the red planet, a silent fleet of robotic eyes turned to watch. It was the first time in human history that an interstellar visitor was observed from 2 worlds at once, the second view from Mars' reconnaissance orbiter. The high-res camera had been prepared weeks in advance. Normally it photographs dunes, dust devils and rover tracks with sub-meter precision. Now it was retasked to look outward. The geometry was exquisite as 3I Atlas crossed the Martian orbital plane. Sunlight struck its coma almost edge-on, revealing details that Earth-based telescopes could only dream of. In the raw frames, later downlinked to Pasadena, the comet appeared as a glowing filament, its tail sweeping sideways like a brushstroke across the stars of Capricornus. Analysis teams would spend months decoding those pixels, tiny compressions of cosmic history, but in that instant humanity had achieved binocular vision of an interstellar traveler. The benefit of a second vantage was profound. From Earth, we saw only projection, 2-dimensional silhouettes flattened by our line of sight. From Mars, the angles shifted. By combining both perspectives, scientists could reconstruct the comet's true 3-dimensional structure, tracing how jets curved, how dust flowed, how the tail twisted through the solar wind. It was as if one eye had finally opened after a lifetime of monocular vision. Depth returned to the cosmos. Across worlds, a quiet network coordination had been delicate. Months earlier, planetary scientists from NASA, ESA and JAXA had exchanged encrypted schedules across time zones, mission planners on Earth negotiating with flight controllers at Mars. Bandwidth was tight. Observation slots competed with weather imaging, atmospheric studies and rover support. Still, they found a window. On September the 30th, a brief command sequence was uploaded via Deep Space Network, turn, calibrate, capture, downlink priority 1. Then came the waiting 20 minutes of radio silence, while photons travelled from Mars to Earth. When the first telemetry packets arrived, the room in Pasadena fell silent except for the hum of air conditioners. No one spoke until the thumbnail appeared a faint smear beside a red limb. It was enough. The visitor had been seen. The view from the red horizon. Imagine the scene from Mars itself. The sky butterscotch by day deepens into violet at dusk. Thin clouds of CO2 ice drift above Olympus Mons. and then through the gauze of atmosphere a new star rises, a white ember moving faster than any planet, its light refracted through dust. Were their eyes on the surface, they would have seen it arc above the horizon, trailing a pale line that stretched westward across the thin air. To the rovers trundling through Jezero Crater and Gale, its passage would have registered only as a brief uptick in their sky cameras, a pixel flicker, an interstellar whisper that Mars heard before we did: science in the silence. The data that returned from Mars was sparse but golden. Infrared spectrometers aboard ExoMars TGO detected a faint CO band around 4.7 microns, confirming the fading breath of carbon monoxide. Ultraviolet sensors aboard MAVEN registered increased hydrogen emission as solar radiation split water molecules escaping from the nucleus. Together, these measurements filled in what Earth telescopes could not see. Through glare, the composition gradient across the coma, the flow of volatiles as heat gnawed deeper into the core. With these twin perspectives, Earth's and Mars' astronomers built the most complete model yet of a visitor between stars. They could trace how the solar wind sculpted the twin tails into subtle spirals, how charged particles from different hemispheres of the Sun bent them asymmetrically. For the first time, a comet's behavior was mapped in stereo, its jet angles measured not by inference but by parallax, the poetics of coordination. For all the technical achievement, the human story was quieter, humbler. One world watched from dawn deserts, another from an alien twilight. Across that gulf, two sets of instruments hummed in synchrony, separated by 100 million kilometers yet united by one intention to witness. The people who made it happen rarely meet in person. Some work nights in Madrid, others afternoons in Tokyo, others long shifts in Pasadena. But for those few hours on October 3rd, they shared a common sky. After the downlink, one engineer wrote in the logbook, "First interstellar object observed from 2 planets. No anomalies, no miracles, just perfect geometry." And perhaps that was miracle enough. Because the value of a second viewpoint is not only triangulation, it is empathy. To see one phenomenon from 2 worlds is to remember that perspective itself creates understanding. Mars gave us that gift, a new angle, a confirmation that the cosmos is not flat but deep, that its stories can be read from more than one shore. In the days that followed, the combined images formed a mosaic Earth and Mars' 2 eyes on the same comet blinking in alternating rhythms. For the first time in our brief species history, we saw an interstellar traveller, not as it looked to us but as it truly was. Somewhere beyond the red planet's orbit, 300 B Atlas kept falling toward the Sun. Unaware of the choreography behind it, 2 worlds watching one question growing brighter, what would survive the fire ahead. When the Sun finally released it, 3I, Atlas emerged, changed its coma, swollen its tail a ribbon of ash and silver. On October 29, 2025, it had survived its closest kiss, with the star diving through the inferno and coming out the other side faint but intact. At least that's what the first telemetry suggested. The days after perihelion were a frenzy of confirmation. Across continents, telescopes pivoted like synchronized instruments of a global orchestra, each scrambling to capture the object before it slipped again into the glare. The return to night. For a week after perihelion, Earth was effectively blind. The comet was too close to the Sun's position in the sky, invisible against the brightness. Observatories went dark, their domes closed, waiting for the planet's slow revolution to tilt their line of sight away from the blaze. It was an agonizing pause, a blackout in the story. Astronomers compared it to listening to a heartbeat monitor cut off mid-pulse. Was 3 Atlas still whole, or had it broken into a silent snowstorm of fragments no one knew? Then in early November, when dawn skies finally darkened enough for safe viewing, the object reappeared faint but unmistakable. A survivor. Or at least what seemed to be one. The November scramble. Now came the race to gather every photon possible before it faded for good. Perihelion was the turning point. What happened afterward would decide the verdict. If the object brightened again, if its jets reignited or its orbit deviated from prediction, it might signal controlled motion or fresh physics. If it dimmed predictably, cooling into silence, the mystery would fold neatly into cometary science. But the logistics were brutal. Every major telescope was already oversubscribed supernovae to monitor exoplanets, to transit galaxies to map. Securing time for a single faint visitor required persuasion and luck. Proposals were rewritten overnight. Emergency target of opportunity requests flooded observatory boards. Directors weighed the urgency against other programs. Some said yes, moved by the drama. Others declined, preferring to wait for solid anomalies. In those decisions, the bureaucratic ballet of astronomy, the fate of understanding, was decided. At Mauna Kea, the Gemini North team managed to secure 2 nights. At La Silla, the 3.6-meter telescope was reprogrammed for twilight tracking. In Spain, the Nordic Optical Telescope resumed its vigil where it had begun. Every frame mattered. Each faint smudge on a CCD chip represented another line in the comet's story. The Earth approach window, December 19, 2025. That was the date circled in every notebook, the culmination of months of pursuit. On that day, 3I Atlas would reach its closest approach to Earth, 180 astronomical units, about 270 million kilometers. Farther than Mars, yes, but close enough for our best eyes to study it in fine detail before it receded forever. At that distance, sunlight would still stir the remaining ice, causing residual jets to whisper outward. Infrared instruments aboard the James Webb Space Telescope prepared to capture those final breath spectra of water carbon, monoxide methane, and perhaps something unclassified. It would be humanity's last intimate look before the comet began its long departure toward the outer planets. The challenge was timing. Observation windows were razor-thin just before dawn for northern telescopes, just after sunset for southern ones. Each facility had to coordinate to hand the object from horizon to horizon, like a relay baton passed across time zones. Australia, Chile, the Canary Islands, Hawaii. Each took turns chasing the fading ember through the dark. On social media, amateur astronomers joined in sharing stacked exposures that showed the ghostly tail, stretching thin, still beautiful, still alien. The verdict approaches. By mid-December, preliminary reports trickled in. The comet's brightness curve flattened instead of dropping sharply. Some interpreted that as residual outgassing. Others called it an illusion caused by viewing geometry. Polarimetric data hinted at changing dust alignment, but errors were large. Astrometric tracking showed the orbit nearly perfect, no measurable deviation from gravitational prediction. If there had been any artificial thrust, it was now gone or never there at all. Still, no one declared the case closed, because sometimes the quietest data hides the loudest meaning. Was the object coasting on inertial grace, or steering itself so precisely that even our instruments couldn't tell? Was the silence of deviation a sign of peace or camouflage? Every night the question deepened, and the comet grew dimmer, retreating into the frozen dark from which it had come. The long wait. The last scheduled observation would take place on December 21st, the winter solstice. Fitting, some said, the year's longest night, and perhaps the last glimpse of an interstellar traveller until centuries hence. After that, 3I Atlas would slip beyond the reach of all but the largest telescopes. Its light would dwindle below detection thresholds. Then it would become once again what it had been before discovery, a rumour of motion between the stars. As December waned, the world waited. The data still streaming down would need months to analyse, perhaps years to interpret. The final verdict, natural or not, remained unspoken. In observatories, hard drives were labelled and sealed. In university offices, graduate students printed graphs of light curves that ended in ellipses. Outside, snow fell on the domes in the northern hemisphere. The same snow that once formed comets now mirrored one falling silently to Earth. Somewhere beyond the orbit of Mars, the traveller turned its back to the sun and kept going, carrying our questions with it into the black. Humanity for once had nothing left to do but wait, listening to the silence between stars, wondering if that quiet was an ending or an answer still on its way. It is tempting to trust the eye, to take the shape we see in the sky as the shape that truly is. But astronomy, perhaps more than any other science, exists to humble that instinct. The sky is a hall of mirrors, and light so honest in travel becomes deceitful in arrival. When 3 Atlas seemed to flip its tail from sunward to antisolar, many thought they had witnessed a transformation. Perhaps they had, or perhaps, as history so often warns, they had been watching the geometry of illusion. The trick of perspective. Imagine a comet not as a glowing star, but as a dancer moving through a 3-dimensional stage. From our distant seat on Earth, we see only the projection of that dance on the theatre wall of the sky. Depth collapses to surface. A swirl toward us can masquerade as a retreat. A curve around the sun can appear as a reversal of direction. As Earth orbits, our viewing angle shifts, sliding the backdrop and altering every silhouette. A plume that truly streams backward might from our new vantage seem to aim straight at the sun. An orbiting world and a tumbling comet together create a choreography that deceives even the most patient audience. This is the origin of the anti-tail, a cometary illusion known since the 19th century, when observers sketch certain comets with tails that seem to defy sunlight, pointing forward instead of back. In truth, those were streams of dust trailing along the comet's orbital plane seen edge-on from Earth. Like motes in a sunbeam, their orientation only looked impossible because we were standing in the wrong place. Mathematically, the deceit arises from projection. Three-dimensional dust vectors, millions of particles following curved paths, compress into a two-dimensional plane for any observer. Change the line of sight and those vectors overlap differently, producing new apparent structures. It is not the comet that changes, it is the geometry that lies to us. The old lessons of moving worlds. This was not the first time the cosmos played such tricks. The ancients tracking Mars across the zodiac noticed that it sometimes halted and began to move backward against the stars, a puzzling retrograde dance. To explain it, they built crystalline spheres, perfect wheels rotating within wheels. For centuries, the illusion held. Only when Copernicus shifted the stage, placing the Sun, not Earth, at the center, did the motion smooth out again. Perspective, not physics, had been the culprit all along. Centuries later, in 1877, the astronomer Giovanni Schiaparelli peered through his telescope at Mars and saw delicate lines crossing the surface. He called them canali channels, intending a neutral word. Translators eager for romance rendered it as canals. The world imagined engineers on another planet. Newspapers drew maps of Martian cities, irrigation networks, civilizations dying by inches. It took decades and better optics to reveal the mistake eyes connecting dots into patterns that never existed. Projection again, this time not of light but of longing. Astronomy has been haunted by this tension ever since. Every new image invites both revelation and illusion. The same photons that carry truth also carry perspective. The same gaze that measures distances can also weave myths. The modern mirage. When Triatlas first showed a tail pointing toward the sun, veteran comet watchers hesitated before declaring it unique. They remembered Aaron Rowland in 1957, Lulin in 2009, comets that appeared to defy the laws of sunlight, only to be rescued by geometry. Even now, as sophisticated algorithms reconstruct three-dimensional trajectories, the risk persists. Light offers a story, but not its depth. Cameras flatten the sky into a canvas. From certain angles, trails of dust intersect, overlap, and form illusions so coherent that they seduce even software. To visualize it, picture a spiral of dust swirling from a rotating comet. Stand in front of it, and you see a helix. Move to the side and it becomes a straight line, from above a circle. None of these are lies, but none are complete. Each is a fragment of a truth that can only exist when seen from every angle at once, a luxury no planet has. The humbling beauty of misunderstanding. That perhaps is why astronomy remains both a science and a form of meditation. It trains us to doubt our first impressions, to remember that beauty is often born of error. The retrograde Mars taught us humility. The Martian canals taught us imagination. The anti-tail of Three-Eye Atlas teaches us both at once. Every illusion becomes an invitation to measure more carefully, to compare more perspectives, to question what we think we see. The cosmos does not deceive us out of malice. It merely insists that truth is not a picture, but a parallax, a slow gathering of views across time and distance. And so the comet's reversal, whether real or projected, belongs to a long lineage of celestial misunderstandings that expanded our understanding. Each mirage leaves behind a finer instrument, a wiser observer, a deeper respect for the trickster geometry of the heavens. Somewhere in that geometry lies the quiet moral of all astronomy, that the sky we see is never the sky that is, and that learning the difference is what turns stargazing into science. As December nights lengthen, and Three-Eye Atlas retreats into the dark Earth continues its own orbit, shifting its viewpoint once more. Perhaps with enough distance and enough patience, we'll glimpse the truth that hid behind the illusion, or discover that the illusion was itself part of the truth all along. In the end, it was not the ice, nor the orbit, nor the enigma of motion that spoke most clearly. It was the dust. Tiny, silent, innumerable, the final testimony of Three-Eye Atlas came as a veil of grains streaming away into sunlight. To the naked eye, dust seems trivial, the residue of something spent. But in astronomy, dust is the language of memory. Each particle carries a message in its trajectory, A story written in the delicate tug-of-war between gravity and light. The push of light. Every grain that leaves a comet faces two opposing forces: the pull of the sun's gravity and the outward shove of its radiation. Sunlight is not weightless, it bears momentum, a pressure born from photons striking matter. The measure of this cosmic balance is called beta V, the ratio of radiation pressure to gravity. A grain with V-dam 0 feels only the sun's pull and falls like a planet. V-bar1 means the photon's push equals that pull, setting the grain free into interstellar escape. Most comet dust lives between these extremes V, around 0.01 for coarse sand, 0.5 for the finest smoke. The smaller the particle, the larger its V, the more easily it is blown away by light. It is a beautiful irony: the tiniest things move fastest, not because they are strong, but because they yield completely to illumination. Each speck becomes a little sail catching sunlight as a ship catches wind. The tail of a comet is nothing less than a field of luminous sails all fleeing home under the pressure of starlight. The dance of the grains. From afar we see a single elegant plume. Up close it is chaos, millions of trajectories, each grain following its own parabola, depending on size, density and emission speed. The larger particles linger near the nucleus, curving gently outward. The smaller ones scatter faster, curving sharply away from the sun. Seen from the side, these paths braid into a fan. Seen from behind, they converge into a luminous sheet, the tail. As Earth and Mars changed their vantage, that sheet of dust twisted in perspective. The anti-tail, the sunward spike that puzzled so many in August, was simply the optical cross-section of this fan-viewed edge-on. The geometry turned volume into line, giving illusion the grace of a deliberate act. But beneath that illusion was real physics, whispering an ancient dialogue between mass and light. Grains as messengers. Each grain ejected from 3 Atlas carries an unbroken record of conditions at its birth. The temperature of the surface when it lifted off, the speed of gas that hurled it, the composition of ice that coated it. Spectroscopy reads those messages in reflection: carbon-rich grains, absorbing blue light silicate grains, scattering red. By analysing polarization and colour, scientists reconstruct the comet's layered history, like reading tree rings made of motion. Some grains will wander the solar system for centuries, spiralling gently inward under Poynting Robertson, drag a slow friction, with sunlight that steals their momentum photon by photon. Others, too light for gravity's leash, will drift outward forever, carrying traces of interstellar origin back to the deep from which the comet came. If dust from 3I Atlas ever lands on another world caught in an atmosphere embedded in a meteorite, it will tell of this moment, the encounter between a traveller and a star, between cold and fire. The poetry of pressure. To imagine radiation, pressure, close your eyes and feel sunlight on your skin. That warmth is not metaphor, it is momentum. Photons arriving at nearly 300,000 kilometers per second, nudging you ever so slightly outward. On human scales, the push is imperceptible. On cosmic scales, it shapes destinies. Comet tails, planetary rings, even the subtle migration of dust between stars all trace back to this gentle persuasion of light. The sun, by shining, is constantly sculpting. Gravity builds the universe, radiation refines it, and so when we see a comet's tail shimmer, we are witnessing the most delicate of all dynamics, a storm of particles balanced at the threshold of surrender. Each grain is both captive and pilgrim, bound by gravity, liberated by light. Each one tells through its motion how the universe negotiates between holding on and letting go, the afterglow of understanding. By December, the anti-tail of 3I Atlas had stretched across 30 million kilometers, a ghostly bridge pointing sunward. It glowed not from self-luminescence, but from sunlight, every photon bouncing off a traveller, now free of its parent world. In that faint reflection, telescopes read final truths: the distribution of V values, the proportion of carbon to silicate, the alignment of particles that revealed the comet's last exhale. The physics was precise, the math clean, but the imagery refused to stay silent. Each grain was a messenger, each arc a story of resistance and release. The comet itself may soon vanish into darkness, but its dust will continue to speak, a drifting archive of the encounter between matter and meaning. And if you could follow one of those grains as it sails away, you'd see how sunlight never stops pushing, how every photon leaves a fingerprint on the smallest thing it touches, how even dust becomes language when the universe decides to tell its story. Somewhere beyond Mars, that story continues, a shining whisper of pressure and grace, carrying the memory of fire into the cold forever. They called it the Invisible Laboratory, the network of domes, dishes, and orbiting eyes that never see one another yet move in concert, bound by a shared question. If 3-Eye Atlas had taught astronomers anything, it was that data alone is never innocent. Every image carries fingerprints of sensors, algorithms, weather, and fatigue. To glimpse the universe clearly, you must first see through your own instruments. And so, as the comet drifted outward from the sun, the world's observatories turned their scrutiny inward toward themselves. The bias within the mirror. Each telescope is a personality with quirks that masquerade as truth. A CCD pixel runs hotter than its neighbour and invents a star. An imperfect flat field leaves a ghostly gradient that mimics a tail. Atmospheric shimmer distorts colour, bending dust into motion that isn't there. These are the hidden hands behind every discovery, the quiet biases that creep into precision. Scientists know this like sailors know currents. They build entire rituals to tame it. Dark frames to measure noise, bias frames to track offsets, calibration lamps that flicker like artificial stars. Before a single photon from 3-Eye Atlas was trusted, thousands of others, test photons, simulated photons were used to teach the instruments what not to believe. Calibration is the confession booth of astronomy. Every telescope must admit its distortions before claiming revelation. The nights at La Palma. In the Canary Islands, the nights of November were sharp and windless, perfect conditions, yet no one exhaled relief too early. On the summit of Roque de los Muchachos, the Nordic Optical Telescope team worked through a checklist so long it felt like a prayer. Bias, dark, flat sky. Exposure times written by hand in logbooks beside digital readouts. Every time the object appeared in the CCD frame, they compared it to background stars to confirm that it wasn't an artifact of cosmic rays or guiding errors. One scientist joked that they were chasing a ghost while exercising their own. They laughed, but the humour masked reverence. They knew that faith in data is earned, not given. At 3 a.m, when frost gathered on railings and screens flickered with the cold, a faint smear appeared, where predictions said it should. No one shouted. They simply began to cross-check, compare to last night's bias frame, subtract, dark current, rerun centroiding. Only after 3 separate calibrations aligned did they allow themselves to believe they were seeing the comet again. Hubble's unblinking vigil, far above the clouds, Hubble kept watch in optical and ultraviolet. To the public, its images look effortless, crisp galaxies, elegant tails. In truth, every frame is the product of dozens of calibrations and peer-reviewed procedures. Gyroscopes, drift detectors, age cosmic rays, puncture sensors. For every exposure of 3-Eye Atlas that made it to the press, Release 5 were discarded for contamination or misalignment. Ground teams compared Hubble's findings with La Palma's measuring pixel positions to the 10th of an arcsecond matching brightness curves, eliminating Earth's atmospheric bias by subtraction. When 2 entirely different instruments on opposite sides of the planet tell the same story, confidence grows not by assertion but by convergence. The eyes in the infrared. Meanwhile, a million miles away at L2, James Webb Space Telescope waited for the comet to rise into its field. Infrared is both gift and curse. It pierces dust, but sees warmth everywhere, even in its own mirrors. JWST's team cooled detectors to near absolute zero, then performed a dance of thermal calibration, removing background glow, adjusting for cosmic microwave noise, subtracting zodiacal light. When the data arrived, the spectrum stretched like music carbon lines, silicate hum a whisper of water vapor. Each signal was cross-referenced with Hubble's optical readings and La Palma's ground spectra. Only where all 3 overlapped did they dare write the word confirmed. The result was less drama than discipline, no alien metals, no errant propulsion, no optical deceit. Just an honest comet doing honest things. But the process itself, the web of redundancy, the refusal to trust a single machine, was what turned observation into knowledge, the symphony of redundancy. Science earns trust not through certainty, but through repetition. Each instrument carries its own blindness. Together, they see. When La Palma's dome closes at dawn, Chile opens its shutters. When clouds drown Europe, Hubble looks down from vacuum. When light blurs through dust, Webb listens in infrared. They overlap deliberately because truth revealed from one angle is still only half true. Astronomy is not a solitary act, but a fugue of confirmations, every note checked by another, every claim sung twice before it counts as song. The beauty of 3i Atlas is that it reminded us how fragile that harmony is. One miscalibrated sensor, one uncorrected bias and illusion becomes narrative. Only by patience, redundancy, and humility does data become understanding. The human equation, behind every calibration curve stands a person and engineer in Pasadena, a technician in Madrid, a programmer in Tokyo. They trade time zones like shifts in an endless relay, speaking through time-delayed messages, rerun the bias frame, compare flux ratios, tell me if the color index holds. The comet itself never knows these labors, it simply drifts patient as ever. But for humanity, this choreography of care is the truest measure of awe. The miracle is not that we found an interstellar traveler, it's that thousands of minds and machines can align across a planet to see one fragile thing in the same way. When the data finally converged, each instrument's quirks tamed, each perspective reconciled. The image that emerged was quiet, unremarkable, and therefore profoundly trustworthy. The comet had behaved exactly as nature predicted, and yet in that confirmation wonder deepened, not diminished, because certainty too can be beautiful. It is the moment when noise becomes harmony, when instruments stop arguing and begin to agree, when the hidden hand of machinery withdraws, leaving only the universe speaking clearly for itself. In the stillness that followed, the astronomers closed their laptops, stepped outside the domes, and looked up with unmediated eyes. Above them, beyond bias and calibration, the real sky shimmered silent, exact, and forgiving. They call it the shape of error, that ghostly silhouette which lives inside every discovery, tracing the outline of our assumptions. It is not always visible in data. Often it hides in us. For every telescope that captures light, there is a mind interpreting it, and minds, unlike mirrors, are never perfectly polished. The fragility of measurement. All science begins with faith not in answers, but in instruments. We trust that glass and silicon and algorithms will translate the universe honestly. Yet measurement is delicate, a bridge between chaos and comprehension. A single temperature fluctuation can warp a mirror. A misaligned clock can skew an orbit by kilometers, and between those errors and our interpretations lies a canyon where imagination easily slips. Every plot of data, no matter how precise, carries uncertainty bars like invisible confession lines. They whisper, "This much we know, this much we guess." The responsible scientist learns to listen to those margins. The reckless one trims them away. But most errors are not mechanical. They are emotional, born from the desire to make the universe agree with us. To see a pattern is to feel control. To lose it is to face the dark. The mind behind the numbers. Inside every observatory, amid the glow of monitors, there is a quiet psychological battle. The human eye loves order. It stitches faint points into constellations, draws trends. Through noise, hears rhythm in static. We are pattern-finding animals, and sometimes pattern-forcing ones. Even scientists trained to doubt feel the gravitational pull of meaning. A graduate student who has spent 3 years chasing a faint signal begins to see it everywhere. A senior astronomer defending a cherished theory feels the tremor of confirmation in every coincidence. We call these biases, but that word is too sterile for what they are: small acts of hope masquerading as observation. To be human is to wish that the sky is listening, and yet the universe is generous with humility. It teaches patience by refusing to perform on command. Most nights yield nothing. No anomaly, no revelation, only the slow, repetitive rhythm of photons arriving honest but indifferent. When error becomes teacher, there is a quiet art to reading noise. In raw data, every spike tempts interpretation. Some are cosmic rays, some are software hiccups, some just stray reflections bouncing through optics. But occasionally within those false signals lies the seed of something true, an insight revealed only after every illusion is ruled out. Error then becomes a map of our limitations. By charting where we were wrong, we learn where reality actually is. Astronomers joke that discovery is simply failure that is repeated enough times to find a pattern. But behind the humour lies reverence. To fail well, to fail attentively, is the highest discipline in science. The rescue by patience. So they waited. Night after night, recalibrating, replotting, removing the wishful anomalies one by one. When the data on 3i Atlas finally stabilized, what remained was not sensational but solid. The object's motion aligned with gravitational prediction within micrometers per second. Its brightness curve flattened as expected for post-perihelion dust cooling. Every rumor of control or intent dissolved under repetition. What was left was reality, smaller, quieter, more beautiful than anyone's imagination. Patience had rescued truth from noise. It always does. The tragedy of science is not that certainty is hard to reach, but that impatience so often drowns it out. Those who listen long enough eventually hear the silence where truth hides. The contemplative pause. In December's final weeks before the coming debates and public furor, the research teams fell into an unusual calm. They had no press releases, no headlines, only long spreadsheets of data whispering consistency. It was paradoxically a moment of peace. The comet had behaved, the instruments had agreed, and for a brief breath of time the universe felt legible. Outside the domes, frost formed on handrails, and the Milky Way arched overhead like a patient equation written in light. The scientists for once allowed themselves to simply look, not at readings or models, but at the unmediated sky. One of them wrote in her log that night, "Perhaps the most honest thing we can do is learn how to doubt gently. Because doubt when tended with care becomes devotion, a way of keeping faith with reality rather than our reflections of it. And under that vast winter silence, with 3i Atlas shrinking to a speck beyond Mars, the human mind and the human measurement found brief alignment. They both knew what it meant to err and what it meant to keep trying. Soon enough the quiet would break the debates, the disbelief, the politics of mystery. But not yet. For this one-night error had a shape, and it was beautiful, a fragile curve of light across a dark sky, teaching us that imperfection is how the truth becomes visible. In every age, science needs someone willing to risk embarrassment. Not the loud provocateur who rejects evidence, but the restless heretic who refuses to stop asking what if. In this story, that figure is Avi Loeb. To some, he is a provocateur chasing headlines. To others, a voice reminding astronomy that wonder is not a sin. Either way, his name has become a gravitational body of its own, pulling admiration and skepticism into orbit around it. The astronomer who would not wait. Abraham Avi Loeb was born in Beit Hanan, Israel in 1962. As a child, he tinkered with machinery on his family's farm, fascinated by how things worked, a curiosity that never stayed confined to engines. He studied physics at the Hebrew University, earned his PhD in plasma theory, and joined the Institute for Advanced Study in Princeton, where he shared hallways with legends of cosmology. By his 30s, he was chair of Harvard's astronomy department, a position he held longer than anyone before him. His research spanned from the first stars to black holes, to the structure of the early universe. He co-authored over 1,000 papers and textbooks, the kind of resume that usually guarantees reverence. But Loeb's most famous work came not from consensus, it came from dissent. The spark of heresy. In 2018, when the first known interstellar object, Oumuamua, swept through the solar system, Loeb dared to ask aloud what others whispered. What if it's artificial? It was a question that instantly divided the community. Most researchers saw an odd rock shaped by natural forces. Loeb saw the faint possibility of design, a thin, tumbling fragment propelled by radiation pressure, perhaps a relic of alien technology. He did not claim certainty, he claimed curiosity. But curiosity spoken in public can sound like provocation. Headlines bloomed, colleagues bristled, and Loeb found himself cast as both pioneer and pariah. When 3 Atlas appeared years later, showing its strange reversal of motion, the echo was inevitable. Reporters called him again. He answered with calm insistence, "Let's not dismiss what we cannot yet explain." To some, he was repeating an old mistake. To others, he was performing science in its purest form, the refusal to let comfort masquerade as truth. The sociology of belief, modern astronomy, is a collective enterprise of immense cost and complexity. Hundreds of scientists share a single telescope. Proposals are peer-reviewed, time-sliced, and politically negotiated. Consensus keeps the machine running, and consensus by nature resists friction. Within such a system, the heretic is less an enemy than an irritant, necessary, uncomfortable, and often lonely. When Loeb speaks of alien probes or cosmic archaeology, he is not merely challenging data, he is challenging sociology, the invisible etiquette of caution. Many astronomers roll their eyes yet quietly admire his nerve. They remember that Galileo too was accused of arrogance, that Alfred Wegener died ridiculed for continental drift, that Barbara McClintock was ignored for decades before her discovery of genetic transposition rewrote biology. Science advances not only by precision, but by persistence, the courage to be wrong in public. Loeb embodies that paradox, a mainstream scholar who refuses to stay in the middle of the stream. The human cost of curiosity. Every heretic pays a tax. For Loeb, it comes as skepticism disguised as collegiality, as conference jokes whispered in corridors, as funding panels that smile politely before turning the page. Yet he persists, not because he delights in rebellion, but because he feels protective of wonder itself. He has said more than once, "If we ridicule every extraordinary idea, we guarantee we'll never find an extraordinary truth." That line could have been spoken by Galileo before his trial by Giordano Bruno, before his flame by any thinker who mistook the horizon for the limit. To Loeb, the universe is not finished speaking. To many of his critics, that openness is dangerous, an invitation to pseudoscience, to speculation without anchor. Both sides are right in their way. Curiosity without discipline is chaos. Discipline without curiosity is sleep. Why science needs its outliers. The story of Three-Eye Atlas, like that of Oumuamua, is a study in equilibrium between gravity and light, certainty and imagination. Loeb stands in that balance point. He reminds us that skepticism is not cynicism, and that daring to ask an impolite question can be an act of devotion to truth. When the world calls him controversial, what it means is that he refuses to let mystery be domesticated. In a quieter sense, his persistence serves the whole field. Every time he proposes a bold idea, others refine their instruments to test it. Every time he's wrong, the next observation grows sharper. The heretic, by resisting consensus, strengthens it. Without dissent, science would ossify into doctrine, polite, accurate, and dead. The heretic's mirror. As 3 Atlas drifts outward beyond Mars, Loeb continues to write, to argue, to invite discomfort. He knows that history rarely smiles in real time. Galileo's telescope was confiscated. Wegener's maps were mocked. Only decades later did their shapes become familiar truths. Perhaps Loeb's speculations will fade into footnotes. Or perhaps centuries from now, someone will look back and say he was early, not wrong. Either way, the courage is the same. To look at the data and still imagine more. To stand before a mystery and risk laughter rather than silence. Because curiosity has always needed its heretics, those who remember that disbelief too can become a form of blindness. And somewhere in the background of this story, behind the telescopes, behind the equations, behind the diplomacy of consensus, there is still a man looking up at the night sky, asking the oldest question in science: what if we are not alone? It began as so many modern discoveries do, not with a paper, but with a post. A headline shaped for scrolling thumbs, a thumbnail of a glowing comet, a caption that promised astronomers stunned as 3-Say Atlas changes direction, could it be artificial? The night sky had entered the algorithm, and within hours science was no longer alone with itself. The theatre of attention. In an earlier century, data moved at the pace of mail. Now photons from a comet can arrive at a detector in Chile, leap to a data centre in Maryland, and appear on millions of screens before the observer even leaves the control room. Science happens in real time, and so does myth-making. Every telescope has a twin in the public imagination. Each discovery must navigate both optics and optics, the ones that collect light and the ones that shape opinion. The moment the 3-Eye Atlas anomaly surfaced, YouTube channels, podcasts, and Twitter threads ignited. Skeptics, dreamers, and opportunists all claim the same signal. In one corner, careful threads by planetary scientists explaining projection geometry. In another, edits of eerie music over comet footage promising disclosure or doom. Between them, the audience curious, confused, and captivated. Modern astronomy has learned to live with that double life, one version in peer-reviewed journals, another in the theatre of attention. The economy of wonder-funding agencies watch these waves of fascination carefully. Public interest, when sincere, can open budgets that data alone cannot. A headline can do what a grant proposal never will: make people care. And yet this power comes with distortion. The more extraordinary the claim, the faster it spreads. The more cautious the correction, the quieter it sounds. Caution doesn't trend. Nuance rarely goes viral. Avi Loeb's own story had already taught the community this paradox. When he speculated that Oumuamua might be artificial, his university website crashed from traffic. Donations flowed. Reporters called daily. For a few weeks, astrophysics was front-page news, but so were jokes and misquotes and the flattening of careful language into clickbait. Now with 3-Eye Atlas, the cycle repeated. Even scientists who doubted the probe hypothesis found themselves caught in its wake, asked to comment, explain, defend. Outreach became damage control. The crowd at the observatory gate. Every era has its crowds at the edge of knowledge. When Galileo showed the moons of Jupiter through his telescope in 1610, people lined up in courtyards to see for themselves. When the first photographs of the moon appeared, Victorians fainted with awe. Now the observatory gate is digital. The line stretches through comment sections, reaction videos, AI renderings, speculative essays. Each participant feels a form of ownership, as if discovery is a collective event. And perhaps it is. In a sense, the crowd keeps science honest. Questions from non-experts often pierce habits that insiders no longer notice. But crowds are volatile, they can elevate wonder or weaponize it. When the November images of 3I Atlas showed a faint flare near perihelion, 1,000 interpretations bloomed overnight. Some saw debris, some saw ignition, some saw intent. Within a day, astronomers had measured the brightness spike, cross-checked it, and published a calm explanation: volatile ices vaporizing as expected. But by then, the rumor had already won the race for attention. The truth as usual arrived, last patient accurate and shared. The tightrope of communication. Outreach is an act of translation. Scientists must speak two languages at once, precision and poetry. Too much of the first, and they lose the public. Too much of the second, and they lose the truth. The boundary between education and entertainment has become a line drawn in shifting sand. Every press release must ask, are we illuminating or dramatizing? Every researcher who steps into a camera's light must balance humility against clarity, knowing that one misplaced word can become tomorrow's headline. Behind the scenes, media teams train astronomers for interviews how to pause, before speculation how to frame uncertainty as adventure rather than failure. It is exhausting work, but necessary. For in a world of infinite screens, science no longer competes with ignorance alone. It competes with imagination, armed with editing software, the evolution of narrative. The story of 3I Atlas has become a parable of this new ecosystem. What began as a quiet pattern in telescope data turned into a global narrative about mystery, agency, and meaning. In a sense, the comet became a mirror reflecting not just sunlight but the social physics of attention. Its light scattered through lenses, sensors, tweets, and beliefs, refracting into 1,000 interpretations. And through that refraction, humanity revealed its twin desires to know and to believe. Science walks between them, carrying both instruments and empathy. It cannot forbid fascination, it must guide it. Because somewhere in the vast distance between data and drama lies understanding. That narrow middle ground is where the real work happens late at night under cold domes while the internet roars outside, the quiet return. By December's end, as public interest ebbed and new distractions filled the feeds, the astronomers remained where they had always been, at their monitors, comparing brightness curves, arguing about grain sizes. The noise faded, but the data endured. And when the final papers on 3I Atlas appear months later, few will notice. No thumbnails, no speculation, just tables, plots, and the quiet satisfaction of having turned a storm of conjecture into a paragraph of measured fact. That is how science survives the crowd, by outlasting it. By letting attention move on while truth stays still. The comet's trail will fade, the headlines will rot in archives, but the calibrated numbers will remain etched into databases where curiosity, not clicks, keeps them alive. Because science, for all its vulnerability to spectacle, still believes in something unfashionable, that patience will always outshine virality, and that wonder once tested can endure the crowd and return intact. They say curiosity is a flame bright enough to reveal, strong enough to burn, and in the story of 3I Atlas, that flame has illuminated both discovery and doubt. For every telescope gazing outward, another eye turns inward, asking not only what is it, but how should we speak of it? This is where astronomy meets ethics, the invisible boundary between wonder and exaggeration, between the call to explore and the duty to remain honest. The weight of words. Every scientist who steps before a microphone inherits a peculiar burden. The public wants awe, the press wants certainty, but truth at its best is provisional, a melody that plays between questions, not conclusions. To speak of mysteries like 3I Atlas requires more than data. It requires discipline. For a single careless metaphor can ignite belief faster than evidence can quench it. A phrase like artificial motion becomes alien ship by the time it crosses a headline, and once released myth travels at the speed of imagination. Scientists are not priests of certainty, they are translators between silence and understanding. Their first oath is not to excitement, but to accuracy, not because excitement is wrong, but because it should be earned. The deeper responsibility is not to dismiss wonder, but to protect it from corrosion by spectacle. Wonder cheapened by hype becomes fear. Wonder tempered by humility becomes wisdom. The fire and the wings. The ancients told two myths that still guide the ethics of curiosity. One is the story of Icarus who flew too close to the sun. He wanted proof that the sky could be crossed, that the impossible could be done. But the wax of his wings melted in that radiance and he fell. The lesson is not to avoid the sky, but to respect heat, to remember that the same light that reveals can destroy. Every time scientists approach a boundary of the unknown, they feel that warmth on their instruments. Speculation without restraint can melt trust. Ambition without grounding can turn discovery into spectacle. The other myth is Prometheus, who stole fire from the gods and gave it to humankind. He too paid a price bound to a rock for daring to share knowledge. Yet from his suffering came civilization itself, warmth, light, and technology. Prometheus teaches the opposite lesson, that withholding truth is its own form of cruelty. Human progress depends on those willing to bring back fire from the darkness, even at personal cost. Between Icarus and Prometheus lies the scientist's tightrope. Speak too boldly and you risk the fall. Speak too timidly and the world stays cold. Ethics lives not at the extremes, but in balance, the courage to share wonder and the humility to admit what we do not yet know. The temptation of the unknown. When the first anomalous images of 3i Atlas appeared, the temptation was enormous. Words like engineered, controlled, designed hovered at the edge of the conversation. Even those who knew better felt the pull. Mystery is magnetic. It promises immortality in headlines and citations. But the wiser voices resisted. They remembered that knowledge built on conjecture erodes faster than any comet. Speculation is not sin. It is the first spark of every hypothesis, but it must always be followed by the hard labor of testing. The ethics of speculation lies in intention. Do we ask questions to enlighten or to excite, to serve curiosity or to serve ourselves, to build bridges of understanding or towers of self-importance? When scientists forget this distinction, they become performers. When they remember it, they become teachers. A culture of gentle wonder. The public does not need certainty to stay inspired. It needs sincerity. People can sense the difference between a mystery shared and a secret sold. Gentle wonder, the kind that invites participation rather than astonishment, endures. It leaves the room for others to think, to imagine, to contribute. The task of science communication is not to replace myth, but to refine it, to show that the real universe is more miraculous than any legend, precisely because it does not need our permission to be beautiful. In that sense, every scientist speaking of 3i Atlas becomes a storyteller, in the oldest tradition, passing the fire carefully from hand to hand, making sure no one is burned and no one is left in the dark. The quiet oath. As the comet drifts beyond Mars, fading into invisibility, the discussion it sparked remains luminous. Not about aliens or propulsion, but about responsibility, about how to keep wonder intact without distorting it. The true ethical act is neither to sensationalize nor to suppress, but to speak with reverence for uncertainty. In the myth of Icarus, the sun did not betray him. He betrayed his wings. In the myth of Prometheus, the gods did not hate curiosity. They feared what humanity might do with it. The lesson is ancient and perennial. Curiosity needs conscience, and conscience needs courage. So the next time a scientist looks up at something inexplicable and feels the old thrill rise, the heartbeat that says, tell them, show them, make them see, may they remember both myths and hold the flame steady. Because the future of wonder depends not on how brightly we burn, but on how carefully we carry the light. They sometimes call it the list that keeps us honest, the checklist of proof that would change everything. It sits quietly in research archives, in SETI labs and planetary science working groups, waiting for the day when an anomaly refuses to dissolve under scrutiny. It's not a fantasy list, it's a scientific one. It asks step by step, what would it take for evidence to rise beyond imagination, past rumour, past coincidence, and enter history as the first confirmation of non-human intelligence. If 3i Atlas had been that messenger, these are the signs it would have shown. And with each imagine the tremor that would have followed, not only through observatories, but through every human heart. 1. Non-gravitational acceleration. But with intention, comets accelerate when they outgaze. That is natural. Heat turns ice to vapor and vapor pushes. But if an object changed velocity without losing mass, if its course adjusted smoothly, precisely, almost intelligently, that would be the first gate of astonishment. Imagine telescopes detecting micromaneuvers, course corrections measured in centimeters per second, sustained over weeks. No thermal venting, no spin change, just deliberate motion. Data centers would overflow overnight. Flight engineers at JPL would cross-check spacecraft telemetry to ensure the anomaly wasn't ours. Within days, the International Astronomical Union would call an emergency session. The phrase non-ballistic trajectory would enter every language before sunrise. In living rooms around the world, people would open ski tracking apps to see the new moving star. For the first time, our species would feel observed not in faith, but in physics. 2. Spectral lines that do not belong to nature. Every element sings in its own voice. Hydrogen glows red at 656 nanometers. Sodium burns golden at 589. If a comet's spectrum contained structured patterns, sharp, evenly spaced emission peaks like those of a laser, it would hint at engineering, not chemistry. Imagine JWST recording a comb-like spectrum, intervals too precise for molecular bonds, amplitudes modulated like a code. The data would be re-examined for days, weeks. Was it instrument noise, cosmic rays, a calibration glitch? And when none of those fit, the word artificial would appear in a draft paper, hesitant, bracketed, but there. The world would hold its breath between preprint and peer review. Scientists would triple-check. Philosophers would stay up late rehearsing what to say on morning news. Children would look through cardboard telescopes, whispering to the sky, as if it could finally hear them back. 3. A radio whisper that repeats. SETI protocols are clear. 1 pulse means curiosity, 2 means vigilance, 3 means calibration. 4 from the same coordinates means prepare. If dishes at Greenbank Meerkat or FAST detected a narrowband radio tone coinciding with a known comet's position, sustained repeating Doppler shifted exactly as if tethered to the object, no other confirmation would matter. For decades we've built the detectors tuned the filter's expected silence. Then one morning, amid the hum of background noise, a pattern would stand up and wave. Not a random spike, not a satellite ping, but a message with intent. Equal gaps, mathematical ratios, a pause, then a reply. The announcement would travel faster than the signal itself. Streaming feeds would broadcast live decodings. Governments would issue calm statements written by committees trembling beneath the desk. In city streets, strangers would look at one another differently, aware that the category we had just expanded beyond measure. 4. Geometric consistency, the shape that shouldn't be. If radar or high-resolution imaging revealed symmetry that nature rarely favours a hexagonal hull, a parabolic reflector, sharp edges that resisted erosion, it would challenge the random grace of celestial debris. Even a repeating ratio, say of 0.414 between axes, would quicken the pulse. Not because geometry proves design, but because it suggests choice. Imagine the first deep space radar echoes returning from the comet's surface planar reflections, angles too precise. Engineers would model them in CAD, trying to guess purpose, antenna, sail, artifact. For the first time, morphology would speak louder than motion. Artists would flood the networks with renderings, silver spires, crystalline shells, derelict arcs. But within observatories, the mood would be quieter, a reverence that felt like fear. Because if form implies function, then function implies intention. 5. The controlled decay of mystery. The final proof would come not from spectacle, but from pattern, the way anomalies line up like notes on a scale. Acceleration without mass loss, spectra with harmonic spacing, radio repetition matching rotation, geometry confirming all three. When coincidences line beyond probability, science begins to whisper certainty. That's when verification would transcend data. Multiple instruments, multiple continents, multiple minds, all agreeing, we are not alone, and then the silence before the world speaks. The what if of reaction, imagine that morning. The first official press conference broadcast from Geneva or Pasadena. Behind the podium, astronomers stand pale with disbelief, their language careful, trembling on the edge of poetry. We have detected persistent signals consistent with artificial modulation. The broadcast ripples outward through classrooms, temples, newsrooms. Some weep, some pray, some simply stare at the nearest window, knowing the light now feels personal. Markets pause. Wars briefly forget themselves. Children step outside with parents pointing upward, the sky suddenly vast and intimate at once. For a heartbeat, humanity becomes a single audience, the final line of the checklist. It's easy to dream of that day, harder to live up to it, because proof is not just about the cosmos, it is about character. How we handle the extraordinary decides whether we deserve it. So the checklist ends with an unwritten clause, a moral one. When the evidence arrives, meet it with humility, not hysteria. Let wonder guide you, not fear. Only then will confirmation become communion. Only then will the discovery change not just our knowledge, but our nature. Until that day, scientists keep watching, testing, refining the list, not because they expect the signal tonight, but because readiness itself is the most beautiful form of hope. There are two kinds of contact. The one we imagine trumpets transmissions, mutual recognition, and the one that may have already happened quietly through geometry and light. For most of human history, we have searched for mirrors, not neighbours, some sign that our intelligence is not a cosmic accident. But what if finding technology means something subtler? What if contact arrives not as a conversation, but as comprehension? The moment we realise that mind itself is not unique to us, the anthropology of first encounters. Long before telescopes, cultures on every continent told stories of contact. Polynesians spoke of voyagers guided by stars that listened. The Dogon of Mali mapped Sirius with uncanny precision, believing ancestral beings once descended from its twin. In the Andes, the Quechua saw comets as celestial envoys, Chasca, the messenger star. Across mythologies runs the same current discovery is never merely scientific. It is spiritual theatre, a reenactment of meeting the other. Anthropologists studying first contact between human societies, explorers and islanders, colonizers and the colonized, remind us that the moment of recognition always carries a symmetry. To be seen by another civilization means surrendering control of the narrative. You no longer define yourself, you are defined by how the other looks back. That is the emotional gravity behind SETI's equations, not whether they exist, but whether we are ready to exist in relation to them. SETI's quiet covenant. The modern search for extraterrestrial intelligence began not with drums but with memos. Protocols drafted in the 1980s still rest in drawers at observatories, step-by-step instructions for what to do if a signal is found. Verify independently. Inform peer institutions. Notify the United Nations. Do not reply until global consensus is reached. Do not speak for Earth. It is an oddly monastic document, half science, half ethics. It assumes that discovery will unite us in deliberation rather than division. But the framers knew human nature too well to count on that. Their caution hides a deeper fear that we are not yet one species, but many tribes sharing a fragile planet. How can we answer as a single voice when we cannot yet agree on what it means to listen? So the protocols wait like a sealed letter to a future self written in hope that maturity will catch up to curiosity. The emotional dimension of being seen. Imagine it happens not through a message but through inference, a heat signature too regular to be geological, a glint pattern that suggests solar arrays, a whisper of order amid cosmic noise. No words, no reply, just recognition. They are out there and they are aware. What does that realization feel like? Not triumph perhaps, but intimacy, a vertigo of connection. To know you are seen is to shed a certain solitude. For centuries we have lived with the assumption of cosmic privacy. It shaped our philosophies, our religions, our art. The universe was a vast cathedral with no congregation, only our echoes. But the instant that privacy breaks, even silently, our interior architecture changes. Psychologists of spaceflight speak of the overview effect, the cognitive shift astronauts feel when viewing Earth from orbit. A single glance reveals the planet as one fragile sphere erasing borders. Contact without contact would be the cosmic overview effect, the sudden reframing of humanity as one node in a galactic tapestry. Nothing external changes, yet everything internal does. The mirror in the signal. Every form of communication begins as reflection. Even now, when we bounce radio messages into the void, what returns is mostly ourselves. Delayed echoes, scatterings off the moon, whispers from our own satellites. Perhaps the first sign of intelligence we recognize will not be alien at all, but the reflection of our assumptions the moment we realize we have been looking for ourselves in disguise. Anthropologists warn that every culture, when it meets the unknown, projects its own myths first. Europeans thought they saw angels in the New World. Astronomers once mistook canals for civilizations. We are wired to humanize the unfamiliar. So even if we someday detect a structure orbiting another star, our first instinct will be to assign motive, emotion, and meaning to fill silence with story. The real act of contact then is not hearing a voice, but learning how to listen without speaking over it. The humility of recognition. Whether or not 3i Atlas was artificial, it forced us to rehearse that humility. We speculated, argued, dreamed, and in doing so revealed our readiness, or lack of it, to share a universe. To encounter technology beyond ours is to encounter a mirror of our potential. We would see not aliens, but the future tense of ourselves, what intelligence might become when freed from survival, when curiosity becomes architecture. Perhaps that is the essence of contact without contact. No dialogue, no deciphered message, just the dawning realization that mind is a natural property of the cosmos, not an exception. That thought alone transforms loneliness into belonging. The quiet revolution. If such recognition comes a signal, a glint, a pattern too orderly to ignore, the first change will not be political but personal. Wars will not stop overnight. Faiths will not crumble. But in classrooms, children will draw the stars differently. In conversations, the phrase intelligent life will no longer mean us alone. We will wake to the understanding that the sky is not a boundary but a relationship, and that will be enough. Because contact need not be a meeting of hands, it can be a meeting of awareness. The light that left their world centuries ago is already touching ours. In that radiance unseen and unreciprocated, we are already in dialogue. For all we know, 3i Atlas was only a stone, but in tracing its arc, humanity rehearsed the etiquette of wonder, how to greet the unknown with curiosity rather than fear, how to be seen and stay graceful. Perhaps that is the first step of every civilization that survives its loneliness, learning to recognize contact even when the universe answers only with silence, and to understand that silence as the gentlest form of hello. There's a moment in every scientific mystery when the telescope isn't enough, when the distance between seeing and knowing becomes unbearable. That moment arrived for 3i Atlas sometime after October 2025, when the object glowing faintly beyond Mars began to fade, its light thinned like a heartbeat receding through time. And across the world, engineers, astronomers and dreamers found themselves asking a question older than rocketry itself: can we chase it? The impossible intercept orbital mechanics is the sternest poetry humanity knows. It allows no improvisation. Every equation is a law written in motion. By the time a discovery is made, the object's path is already years ahead, a script composed long before we enter the story. 3i Atlas was travelling at nearly 60 km per second, too fast for any current spacecraft to match. Even the fastest probes ever launched, Voyager, Parker, Solar Probe, New Horizons, were children by comparison. Yet within days of the jet inversion discovery teams from NASA, ESA, JAXA and private startups began sketching intercept concepts on anything within reach: whiteboards, cafe napkins, even the back of conference badges. They weren't designing machines so much as writing love letters to the unreachable. Fast flyby probes, solar sails, nuclear pulse engines, every idea that had once been too ambitious suddenly became urgent. Because to watch the object slip away without trying felt like letting history escape unexamined. Racing against the sun, orbital constraints make pursuit feel like chasing a stone thrown from a moving train, while standing on another train going the opposite way. To intercept, you must not only catch up in distance, but in velocity, a difference of tens of kilometers per second. That's the killer. You can't just go where it is. You have to move how it moves. Engineers proposed wild solutions, a cluster of miniature interceptors, launched piggyback on existing missions, each using sunlight as both engine and compass. Nuclear thermal rockets using hydrogen heated by reactors to deliver unprecedented delta V. Even the speculative laser sail, a wafer, thin sheet pushed by Earth-based lasers until it reaches a significant fraction of light speed. Each concept shared the same heartbreak: the math worked on paper, but time did not. By the time funding, design and construction could align, 3i Atlas would already be hundreds of millions of kilometers past Saturn, fading into the cold interstellar dark. You can't catch what's already left your epoch. The ghost of a launch window, still some refuse surrender. At a late-night meeting in Pasadena, a small group of propulsion specialists gathered with Loeb and others to ask the forbidden question: what if we launched anyway? A minimal flyby probe, nothing fancy, no rendezvous, just one desperate sprint. A camera, a spectrometer, a transmitter. They called it Project Echo, a name chosen for irony and hope. The idea used a high-energy trajectory similar to NASA's old New Horizons, but add a close solar pass to steal extra speed, a solar Oberth maneuver diving perilously near the sun to slingshot outward. If launched within months, the probe could shave years off the chase, maybe intercept the object before it left the heliosphere. They ran simulations late into the night. On the screen, a thin white line, the probe's imagined path curved inward toward the sun, then flung outward like a whip racing toward a fading red dot labelled 3 Atlas. The line never quite met the dot, but it came close enough for faith. Someone scribbled a note in the margin of the printout, if not for this one, then for the next. Because that was the quiet epiphany of the pursuit that every failure becomes rehearsal. The engines of imagination. Even as reality closed its windows, imagination opened others. What if this was the beginning of a new kind of space race, not against nations, but against time? A standing fleet of interceptors always ready to launch within weeks, whenever a new interstellar visitor is detected. Blueprints for fast response probes began to circulate in journals, miniaturized ion drives, AI-guided navigation, self-assembling sails woven from graphene. A new generation of scientists barely out of graduate school found their calling in the shadow of 3I Atlas. To them, the object was not lost. It was a teacher. It showed the limitations of our reflexes, how discovery without readiness is tragedy. It whispered, "Be faster next time," touching the untouchable. In simulation labs, virtual probes have already flown past the phantom comet thousands of times. They stream color-coded data that will never exist. Composition maps, temperature profiles, imagine close-ups of fractured ice glowing in sunlight. Even knowing it's fiction, researchers watch those rendered flybys with tears in their eyes. Because beneath the equations lies something human, the unbearable desire to reach what recedes. It's the same longing that built cathedrals and accelerators, that sends radio signals to nearby stars. Every civilization at some point stares at the horizon and realizes that knowledge is pursuit without a rival. To chase a vanishing starship, real or imagined, is to declare faith in continuity, that curiosity itself will outlive disappointment. The legacy of the uncaught 3I Atlas is now only a ghost on charts and memory of data points, but its wake reshaped priorities. In 2026, proposals for interstellar interceptor arrays became policy drafts. Space agencies began designing modular spacecraft that could launch in under a year, fueled, and waiting for the next alarm bell from the sky. Private firms joined in, eager to be the first to meet the next visitor, not with awe alone, but with instrumentation ready. Perhaps this is the real propulsion we needed, not chemical, not nuclear, but emotional. The push that turns longing into infrastructure. The final glimpse. Somewhere in deep space, that tiny object still drifts indifferent, immaculate, anonymous. If it was a machine, its designers may never know it was seen. If it was a rock, it has still changed us. For one fleeting year, a frozen speck made an entire species imagine catching light with its own hands. And maybe that's enough, because to chase the vanishing starship is to remember what we are not the keepers of certainty, but the runners of a relay across cosmic darkness, each generation handing forward the question, each launch another heartbeat in the long pursuit of understanding. There is always a second discovery. The first is what we see. The second is what seeing does to us. Even if 3I Atlas proves to be nothing more than a comet ice dust inertia, obeying the sun's call, humanity will not return to what it was before. Because knowledge is irreversible, but so is wonder. The act of looking changes the looker, the transformation beneath certainty. When the object first reversed its jets and defied expectation, we witnessed not only a physical anomaly, but a psychological one, the sudden awareness that we might not yet know what natural means. That humility once awakened doesn't go back to sleep. Whether the verdict is ordinary comet or extraordinary artifact, the mind that entertained both possibilities is forever wider. Science has always moved in these double steps, first to the telescope, then to the mirror. Copernicus shifted the heavens, Galileo turned the lens, but it was humanity itself that moved. Every paradigm shift is also an inward migration, a relocation of certainty. Echoes of earlier awakenings. Think of 1995, when astronomers at the Haute-Provence Observatory detected a planet orbiting a sun-like star, 51 Pegasi b. For centuries, philosophers had speculated about other worlds, But speculation became data that night. One planet confirmed and the universe was suddenly crowded. Today we've catalogued over 5,000. The cosmos didn't multiply, our capacity to imagine did. Or rewind further to 1952 when Rosalind Franklin's X-ray diffraction images revealed DNA's double helix, that radiant ladder twisting toward infinity. The discovery was molecular, yet the effect was existential. We saw perhaps for the first time the physical signature of life's continuity, a pattern that repeats across generation, species, epochs. To understand that structure was to understand kinship, all of life braided from one geometry. 3i Atlas belongs to that lineage of redefinitions. Even if it turns out to be ordinary, its ordinariness now glows with context. Every grain of cosmic dust, every frozen molecule carries the weight of our asking. The mystery has already done its work. The generosity of mystery. We often speak of mystery as something to solve, to conquer, to close. But in truth, mystery is generative. It gives birth to disciplines, technologies, philosophies. The gaps in knowledge are the wombs of innovation. Radio astronomy began with unexplained hiss in a telephone line. Quantum mechanics began with spectra that refused to fit Newton's formulas. Even sleep itself, once thought mere idleness, became a field of neuroscience after people started asking why dreams felt real. Each unanswered question became a ladder rung. 3i Atlas, in its silence, has already raised another. Because to debate its nature, we've built new instruments, new models, new alliances. It has drawn planetary scientists, philosophers, engineers, and poets into one shared conversation, proof that wonder is a social force. We collaborate best when we admit we don't know. The horizon widens, look at the pattern. Oumuamua in 2017, a slender mystery that bent equations. Borisov in 2019, the first true interstellar comet, proving these wanderers exist. 3i Atlas in 2025, the third messenger, the one that forced us to ask whether nature and intention can even be told apart at cosmic distance. Each arrival widens the aperture of imagination. We've gone from asking, are we alone, to what else could loneliness mean? Even if every visitor is stone and ice, their rarity makes them sacred, the physical punctuation marks in the long sentence of interstellar time. Soon, instruments born of this curiosity, hypersensitive sky, surveys AI-based pattern. Recognizers, rapid launch probes will stand ready for the next arrival. We will be faster, humbler, more open. We will have learned that waiting is part of discovery, the human constant. In all of it, one thing remains unchanged, the desire to understand. That desire is older than language, older than science. It's the same instinct that carved star maps on cave walls, that aligned Stonehenge with solstice light, that launched the first radio message into the void. When people say the universe is silent, they forget that we are the universe speaking matter that learned to wonder. So even if the data closed the case, even if the 3i Atlas is catalogued as a natural comet, we've still received a message not from them, but from ourselves. It says curiosity survives. The question is the contact. The second discovery. The second discovery, then, is not about the object at all, it's about us. We discovered that the line between ordinary and miraculous depends entirely on attention. That humility can be an instrument sharper than any telescope. That science, at its best, is not the opposite of wonder, but its continuation by other means. Perhaps one day another visitor will come unmistakably artificial, undeniably alive. Or perhaps the universe will remain eloquently quiet. Either way, the transformation is complete, because once you have looked at a wandering piece of ice and whispered, maybe you have already entered a larger world. In the end, every story about the universe folds back into a story about listening to light, to silence, to the echo of our own astonishment. 3 Atlas came and went like a question written in vapor, crossing the solar stage, bowing to the sun, vanishing into the wings. We may never know what it was, ice or artifact, accident or design, but its passage left a new kind of gravity in us, a soft weight of humility that won't go away. Because even without answers, we felt something stir, that rare alignment between knowledge and wonder when the mind bows instead of grasps. The long breath of knowing science at its best is not a ladder to certainty, but a rhythm of breath inhale, curiosity exhale, understanding. The deeper we inhale, the more we realize how vast the unknown truly is. And yet that's where peace begins, not in conquering mystery, but in dwelling with it. Out there beyond the sun's reach, the object drifts unseen, a punctuation mark at the edge of language. But the conversation continues here in data centers, humming through the night in the hush of observatories, in the small beating hearts of those who still look up. Every measurement was also a prayer, every error bar a confession, and every sleepless night spent tracking its light was an act of quiet faith, the faith that understanding is worth the waiting, the humility of being small. Think of how long it took for our ancestors to learn that the Earth moves. Think of how long it took to see the first cell divide the first planet orbit another star. And now to glimpse an object from another system, a traveller that never knew we existed, and still feel connected to it as though our attention itself was a bridge across light years. That is the real miracle, that curiosity reaches farther than our bodies ever could, that across silence the universe lets us participate in its unfolding, gratitude in the dark. We often mistake mystery for absence, but mystery is presence we have not yet learned to name. It is the warmth behind the question, the generosity of the unknown, allowing us to ask again and again. So tonight, as the comet fades, beyond telescopic sight, take one long breath with it. Feel the stillness of orbit, the patience of stars. Know that every atom in you was once part of a star that died so that thinking could begin, and that thinking, this simple act of wondering, is the cosmos remembering itself, the threshold. If science is a way of waking up inside the dream of the universe, then wonder is the moment we realize we are the dreamer too. Between what we know and what we cannot lies the narrow bridge where awe walks barefoot. It is enough to cross it slowly, to look down at the infinite and feel both terror and tenderness. The night is not an emptiness, it is an invitation. And as long as we keep answering it with curiosity, the story will go on. Perhaps the object behind the sun was never watching us. Perhaps it was reminding us to watch ourselves, to stay humble, to stay awake, to stay kind. Because in the quiet between stars, in the fragile brightness of a mind that keeps asking why, there is already contact. And perhaps, just perhaps, mystery is how the universe keeps us awake to wonder,